At the top of the sky, where blue bleeds into black, it feels like you're staring at the edge of everything. And yet, there's no wall, no fence, no final line. Still, the universe keeps whispering that there is a boundary. So if space doesn't end, what exactly are we reaching for? More space? Absolute nothing? Other universes? Or a reality our physics can't name? We learn early to trust boundaries, shorelines, horizons, the clean edge where one world ends and another begins. Yet the moment a rocket climbs high enough, the atmosphere does not stop. It simply loosens its grip. Molecules thin, sound fails, and sunlight loses its blue scattering until day itself turns ink black. From that height, space feels like a destination, but it is only a change in conditions, an argument about where air becomes too rare to fly. And still, the universe feels bounded. Look outward and you meet a strange kind of edge, one made not of stone, but of time. Every star is a message in transit, and every galaxy arrives as a delayed confession. The farther we see, the further back we are forced to look, until distance becomes a history book written in fading light. So what does it mean to ask where the universe ends, if it ends at all? If there is an edge in any meaningful sense, is it a place you could reach, or a limit you can only calculate? And if there is a limit, what lies beyond it? More space, nothing at all, other universes, or a reality our physics cannot yet describe? This film begins with the most familiar edge, the one above our heads, and then turns it inside out. We will follow the atmosphere through its layered thinning, past the arbitrary lines humans draw for convenience, and into the deeper boundary that no engine can cross. We will meet horizons that move as the universe expands, limits that fence in what light, matter, and information can ever deliver. Beyond those horizons, the cosmos does not necessarily stop. It may simply fall out of contact. There may be more galaxies than any telescope will ever count, regions forever unlit to us by the rules of causality, and traces of earlier epochs hidden behind a last ancient glow. There may be shapes to space that allow finiteness without an edge, and futures where acceleration erases the distant universe one redshift at a time. And beneath every map of the sky, another question waits: whether space is fundamental at all. If space-time can emerge from deeper rules, then the truest boundary is not a line in the dark, but the limit of what any observer can know. The edge of space may be less like a cliff, and more like a mirror, showing us the constraints of our viewpoint, even as it tempts us with what might exist beyond it. What lies beyond the edge of space is not a single answer, but a journey through the best evidence we have, and the mysteries that evidence still cannot reach. We will not chase spectacle for its own sake. We will chase the boundary between what is real and what is reachable. And as we climb from blue sky to black, from nearby planets to the oldest light, one unsettling truth will sharpen: an edge can be absolute without being a wall. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the false edge above Earth to the cosmic horizon, the last light, and the deep rules beneath space-time, each chapter tightens the question. By the end, you'll see why the universe can feel bounded, even if it has no end. We start with a climb that feels like escape, a straight line away from everything familiar. The camera holds on rivets, frost, and vibrating panels, small human details, while engines push against gravity and the planet refuses to let go easily. Inside the cabin, gauges tremble and warning lights blink with quiet urgency, as if the machine itself is counting down each fragile margin. At sea level, Earth's pull is not a suggestion, but a constant demand for energy. Every meter upward costs fuel, heat, and noise, and the rising vehicle writes its path through air that behaves like substance. Drag increases with speed and density, so the climb is a negotiation between thrust, mass, and an atmosphere that resists being parted. In the troposphere, the atmosphere is thick enough to act like an ocean of gas. Clouds billow like slow explosions, turbulence shakes the frame, and weather systems swirl beneath us as if the planet is breathing. Water vapor and dust ride invisible currents, and the camera catches sunlight flashing off ice crystals like shards of glass. Most of the sky's familiar blue is made here, in this dense layer of nitrogen and oxygen. Sunlight arrives as a blend of wavelengths, and the smallest molecules in air scatter the shorter blue wavelengths more efficiently. The result is not a painted ceiling, but a field of redirected photons arriving from every direction at once. That scattering has a name, Rayleigh scattering, and it is not pigment painted across a dome. It is physics acting on light, because tiny molecules interact more strongly with short wavelengths than with long red ones. The math is unforgiving. Scattering strength rises sharply as wavelength shrinks, which is why blue dominates while violet is mostly lost to absorption and our own eyes. The effect is strongest when the sun is high and the light path is short. When the sun is low, the path through air lengthens, blue scatters away, and the remaining light shifts toward orange and red. At sunset, the camera watches the spectrum stretch, gold to amber to bruised crimson, because the atmosphere has sifted the light like a sieve. As altitude rises, the blue thins because there are fewer molecules to do the scattering. The horizon sharpens into a hard curve, and the sky darkens, not from night, but from absence. Even the brightest daytime glare begins to look like a spotlight in a cavern, illuminating the earth while leaving the surrounding sky unlit. Visually, it is a slow draining of colour, like ink diluted in water until it disappears. The blue overhead fades first, then the haze at the edges retreats, and the world below begins to look sealed under glass. City grids and coastlines compress into a map, and the clouds become a textured skin, white scars on a turning sphere. Sound fades for a different reason, and the silence is not mystical. Sound is a pressure wave, and it needs a medium so collisions between molecules can pass energy along. In other words, a sound is a travelling pattern of compression, and without enough particles to jostle, the pattern cannot move. In dense air, those collisions happen constantly, which is why a roar can fill a valley. As density drops, the wave loses its ability to propagate, and the world becomes mute even while the craft still shakes. The last audible traces feel intimate. Straps creak, metal ticks, and the hull transmits vibration like a drumhead. The microphones may still capture vibration through the hull, but the air outside can no longer carry a voice. The silence is not emptiness yet. It is simply the loss of a messenger. Outside the window, the vehicle still plows forward, but the atmosphere is no longer a partner in the conversation. The stratosphere arrives above the weather, layered and stable, where temperature trends reverse. Here, air is stratified, and the lack of convection gives the layer its name and its calm. Jets cruise near its lower reaches precisely because it is steady, and the camera lingers on thin, stretched cloud bands that look combed into place. Ozone absorbs ultraviolet light, and that absorption warms this region from above. The ozone layer is thin in concentration, yet powerful in effect, because it intercepts radiation that would otherwise damage DNA and living tissue. It is a chemical shield built from a rare molecule, created and destroyed in a continual cycle driven by sunlight. Historically, this was not just a scientific curiosity, but a planetary vulnerability. When chemists and atmospheric scientists linked certain industrial chemicals to ozone loss, the discovery reshaped policy and reminded us that thin layers can matter. The story carries a quiet lesson. Global systems can be altered by small concentrations and repaired only with coordinated restraint. The climb continues into the mesosphere, where air is thinner and temperatures fall again. The vehicle's skin meets a different kind of cold, and the sky above deepens toward black. The camera catches a faint limb of atmosphere at the horizon, a delicate gradient that looks almost painted onto the planet's edge. Meteors often burn here because even thin air can heat them at speed. The heating is not friction like rubbing hands, but compression. Air piles up in front of a fast object and converts motion into heat. A meteor's glow is the atmosphere lighting up, as much as it is the rock itself, because shocked gas radiates in a brief, violent flare. A streak of light is a brief equation made visible, a grain of cosmic debris announcing itself. For a moment, the mesosphere becomes a screen where the solar system writes its leftovers in fire. Most of those grains are smaller than sand, yet they arrive with enough energy to mimic a welding arc in the sky. Above that sits the thermosphere, where the word temperature becomes misleading. Individual particles can carry high kinetic energy, yet there are too few of them to warm a human body in the usual sense. The air here is so rarefied that the idea of hot becomes statistical, not tactile, numbers without the familiar sensation. A thermometer exposed here would not behave like one on Earth, because heat transfer depends on collisions. You can have energetic particles and still feel cold because energy is present but rarely delivered. The craft, meanwhile, must still manage heat because sunlight and shadow can swing temperatures sharply when the air no longer moderates them. Auroras glow here as charged particles meet Earth's magnetic shield and excite atoms into light. Electrons spiral along magnetic field lines, collide with oxygen and nitrogen, and the atoms release photons as they relax. The colours are signatures: green from oxygen at lower altitudes, deeper red from oxygen higher up, and purples from nitrogen's contribution. From above, the aurora is not a curtain but a luminous geography, a map of invisible fields. Green sheets ripple, red fringes hover higher, and the planet's magnetism reveals itself in colour. The camera drifts over it like a satellite over weather, and the glow seems to breathe, pulsing with storms on the sun we cannot hear. Then comes the exosphere, the outer fade of the atmosphere into space. Particles drift on long paths, and collisions become rare enough that the word air starts to lose meaning. Some of these atoms can travel for hours without striking another, tracing quiet arcs that resemble orbital motion more than wind. Some atoms follow ballistic arcs and fall back, while others escape entirely, pulled into the long, quiet trade between Earth and space. The boundary is not a door, it is a thinning probability. It is also a reminder that Earth is always leaking, slowly and selectively, into the larger environment around it. This ascent feels like crossing a border, but nature rarely builds borders. Most boundaries are gradients, and the atmosphere is a slow surrender rather than a cliff. The camera emphasizes that surrender, layer after layer becoming less a place and more a trace. Still, we like lines, because lines make decisions feel clean. We name a point where space begins, and we treat it like a doorway with a number on it. That number becomes a cultural artifact, printed on mission patches and stitched into the way we tell the story. The most famous line is the Kármán line, set near 100 kilometers above sea level. It marks the altitude where aerodynamic flight becomes impractical, because the air is too thin for wings to generate enough lift. Past that point, a vehicle must rely primarily on orbital velocity and rocket propulsion, not on the atmosphere's support. The idea traces back to Theodor von Kármán, who asked a practical question about vehicles. At what height would you need to move so fast to get lift that you might as well be in orbit? It is an engineer's definition of space, born not from poetry, but from equations about force and speed. That line is useful, but it is not a wall in the sky. The exact altitude shifts with solar activity, atmospheric swelling, and the assumptions inside the calculation. Even Earth's shape and local density variations matter, so the edge wavers like a contour line on a living map. When the sun is active, it heats the upper atmosphere and makes it expand outward. The same spacecraft can experience more drag on some years than others, because the air itself puffs up and retreats. In extreme cases, satellites must boost their orbits sooner than planned, because a slightly thicker thermosphere can tug them down. Other definitions compete, because different goals demand different thresholds. Some agencies use 80 kilometers, some use 100, and some use functional criteria like sustained orbit. The argument is not trivial. Records, awards, and even safety standards can hinge on where we choose to draw a line. The edge of space changes when the question changes, and that is the point. A pilot cares about control authority, an engineer cares about aerodynamic forces, and a scientist cares about contamination and signal distortion. Each perspective is valid, and each reveals a different way the atmosphere continues to matter, even when it is almost gone. Even the word space can mean different things in practice. For engineers, it can mean where lift fails. For pilots, it can mean where control surfaces lose authority. For scientists, it can mean where the atmosphere stops shaping measurements, because even a trace of air can bend light and absorb specific wavelengths. The boundary becomes an instrument problem, not a philosophical one. A telescope's clarity, a spectrometer's precision, and a radio signal's path can all be altered by thin layers that seem negligible to the eye. In that sense, space begins when the atmosphere stops being an active participant in what we can detect. From the ground, the black above looks like a final boundary. From orbit, Earth's air is a thin shell, a pale limb glowing at sunrise, and the line we imagined becomes a soft gradient. The camera glides along that limb where blue fades into indigo and then into a darkness that is not a place, but a lack. You can see the atmosphere as a faint halo, layered like a lens. It is beautiful precisely because it is fragile, a narrow band that holds oceans down and keeps temperatures livable. The same thin shell that scatters blue light also slows meteors, circulates heat, and makes biology possible. Yet it is, on a planetary scale, almost nothing. The first twist is simple and unsettling. When we say edge of space, we are describing a human threshold, not a cosmic border. Leaving Earth is dramatic, but it is not leaving the universe. It is moving from one region of a continuous cosmos into another region of the same reality. That distinction matters because it changes what edge can mean, and it turns a cinematic ascent into a philosophical trapdoor. A local edge can be a convention, while a universal edge would be a physical limit written into nature. So we widen the question beyond the atmosphere, and the camera widens with it. If there is no physical wall above Earth, is there any wall anywhere? The idea of an edge of the universe persists because our view is limited. We look outward and see a finite sphere of light around us, like a bubble whose surface is made of distance and time. The farther we look, the older the light becomes, until looking outward is indistinguishable from looking backward. This is not because the universe ends there, but because information travels at a speed. Light has a finite speed, and the universe has a finite age since its early hot beginning. There has only been so much time for light to reach us since the beginning, and beyond a certain distance, light has not had time to arrive. That distance defines a horizon, and it is a real boundary in observation. It is called the cosmic light horizon, and it sets the size of the observable universe. The horizon is not a fence in space. Rather, it is a limit in space-time, drawn by the history of expansion and the time available for signals to travel. The observable universe is not a claim about total size. It is a claim about what can be seen from here, given time, expansion, and the speed at which signals can travel. Expansion complicates the story, because space itself can stretch as the universe evolves. Distant galaxies can recede faster than light without breaking relativity, because they are carried by expanding space rather than moving locally through it. In practical terms, there are places whose light is already on its way, and places whose light will never arrive. The horizon is not only about the past, it is also about the future. We can describe this boundary with equations and still feel its strangeness. The universe can be without an edge, yet our access to it can remain bounded by physics. This is the central tension we will carry through the film, because the universe feels finite in what we can see, yet it may be infinite in what exists. When people imagine flying to the edge, they picture a place you could reach. In modern cosmology, there is no known physical edge you could travel to. Like a cliff where space stops. Space, as far as we can tell, does not end at a rim. It can be unbounded like the surface of a sphere, finite in extent yet without an edge, or it can be flat and infinite, extending without limit. Those possibilities sound abstract, but they shape what beyond could mean. Beyond an edge could mean more space, or it could mean nothing, or it could mean a different region of reality. The film's question is not only about distance, but about meaning. If the universe has an edge in any meaningful sense, what lies beyond it? To approach that, we need to separate two kinds of boundaries. One is a boundary in matter and air, like the fading exosphere, and the other is a boundary in information, like the cosmic horizon. The first boundary is crossed by rockets and capsules, by heat shields and pressure suits. The second boundary is not crossed by speed alone, because it is built into time, expansion, and the causal structure of space-time. We can test the atmosphere directly by climbing through it and sampling its particles. We can test the cosmic horizon indirectly by reading the oldest light we can detect and measuring how it has been stretched. That oldest light is the cosmic microwave background, a faint afterglow from the early universe. It is not the edge of space, but it is the edge of our direct view into the past. It began as brilliant radiation in a hot plasma, then cooled as the universe expanded until atoms formed and light could travel freely. Today it arrives as microwaves, nearly uniform, with tiny variations that encode ancient structure. Those tiny variations are not noise, they are a fossil record, the seeds of galaxies written as temperature differences across the sky. Even that boundary is not absolute, because other messengers exist. Neutrinos and gravitational waves can carry information from eras light cannot reach, though our instruments are still learning to listen. So the edge shifts again, depending on what we can measure, and the horizon of knowledge moves with technology, patience, and the willingness to interpret faint signals. This is why the opening ascent matters as more than spectacle. It teaches that edges can be defined, useful, and still not fundamental. The sky turning black is not the universe ending, it is scattering ending. The silence is not emptiness, it is the loss of a medium that once carried pressure waves to our ears. The Kármán line is not a seam in reality, it is a line in our language. It is a way to mark where one kind of motion yields to another, and where engineering becomes orbital mechanics. In the same way, the observable universe is not a wall you could touch. It is a limit set by the speed of light, the age of the cosmos, and the ongoing expansion of space. The unsettling part is that both edges feel real from inside them. From the ground, the atmosphere feels endless until it thins into nothing, and from our place in the cosmos, the visible universe feels like everything, until we admit it is only what has had time to reach us. So we return to the hook at the top of the sky, where Earth looks complete and small. You might think you have reached the edge of everything, because the blue has vanished and the planet seems sealed beneath you. But the deeper truth is that the first edge is a false edge, and it trains us to ask the harder question. If the universe has no obvious wall, why does it still feel like it has a boundary? If our horizon is not the end, what lies beyond what we can see, and what does beyond even mean? The mystery is not only where the boundary is, but why the boundary appears at all. Now we leave the atmospheric threshold behind and follow the idea of an edge outward. We trade the Kármán line for the cosmic horizon, and we ask what kind of universe can hide more than it shows. We left Earth's thinning air behind, but we did not leave the universe. Chapter 1 stripped away a false border, and it left a harder boundary in its place. The sky can turn black without space ending, because the real limit is not altitude. The real limit is information, and the messenger is light. Imagine the camera drifting above the last blue haze of atmosphere. Below, clouds curl like white brushstrokes. Ahead, the stars do not switch on so much as they reveal themselves sharp and indifferent. Darkness is not emptiness. It is simply the absence of nearby scattering. In orbit, there is no air to glow, so the background drops away and the cosmos looks deeper. Light does not arrive instantly, and the universe has not existed forever. Every photon carries a travel time, and distance becomes a record of when it left. When we look outward, we are not seeing space as it is now. We are seeing space as it was because the light is old. That delay is not a flaw in our vision. It is the universe offering its own archive. A photon is a messenger that cannot lie about its journey because its speed is fixed locally. If it takes 8 minutes to cross the gap from the sun, then 8 minutes of history are built into sunlight. If a galaxy's light needs 1 billion years, then 1 billion years are embedded in what we see. This is look-back time, and it is the first true cosmic edge. A nearby star is seen minutes in the past, and a nearby galaxy is seen millions of years ago. A distant galaxy is seen when it was younger, smaller, and still assembling its structure. The farther the light has travelled, the earlier the snapshot we receive. In a deep field image, the effect becomes almost tactile. The foreground stars look like clean pinpricks, but behind them the galaxies blur into tiny smears and warped commas. Some are red and faint, their light stretched thin by the universe's growth. Others are bright knots, compact, violent, still forming their first generations of stars. That simple fact turns the night sky into a layered archive. The present is local, and the deep universe is history stacked behind it. Telescopes do not just magnify distance, they extend memory. Every increase in sensitivity pushes us toward earlier chapters of cosmic time. Sensitivity matters because the oldest light is also the faintest. Flux spreads out with distance, and expansion further dilutes it by stretching each photon's wavelength. Even with perfect optics, you cannot collect what never arrives, so the instrument becomes a kind of time machine with a limited aperture. The deeper we stare, the more the universe demands patience, precision, and cold, dark detectors. The reason this archive has an outer limit is the universe's finite age. Cosmology points to an origin in a hot, dense early state about 13.8 billion years ago. That number is not a guess from one method, but a convergence from several. The expansion rate, the cosmic microwave background, and the abundance of light elements all agree. Time began for our observable region in that early era, and light has been travelling ever since. Historically, this was not obvious, and it was not inevitable. In the early 20th century, Astronomers argued over whether the Milky Way was the whole universe. Then Edwin Hubble measured distances to nearby galaxies and found they were far outside our own. Soon after, the same Hubble saw that their spectra were shifted toward red, an observation that suggested the universe itself was expanding. So it is tempting to say the observable universe should be a sphere 13.8 billion light-years across. That would be true if space was static and distances stayed fixed. But space expands, and expansion changes what a light-year means across cosmic history. The universe has been stretching while the light was in flight. A light-year is a distance, but it is also a reminder that distance and time are braided together. When the universe expands, the yardsticks between galaxies change while the photons are en route. The path is not through a rigid stage, it is through a geometry that evolves. The result is counterintuitive, but it is also measurable. Because of that stretching, the observable universe is larger than its age in light-years. The current radius of the observable universe is about 46.5 billion light-years. The number sounds like a contradiction, but it is a consequence of expansion. The light we receive today started much closer than 46.5 billion light-years away. While it travelled, the space between us and its source grew. Visualize a grid drawn on an elastic sheet, with galaxies marked as dots on the intersections. A photon is a tiny bead sliding along the sheet, always moving at the same local speed. While it travels, the sheet stretches and the distance between grid points increases. The bead still moves faithfully, but the destination recedes in a way that feels like a trick. To keep the logic straight, cosmology separates distance into different kinds. There is the distance light actually travelled through expanding space, measured as a time integral. There is the distance to where the source is now, measured in today's stretched geometry. There is also the distance between 2 points if the expansion were factored out, which is the comoving distance. These are not tricks, they are bookkeeping for a dynamic universe. This bookkeeping becomes essential when you compare objects across billions of years. Without it, you mix then and now in the same sentence, and the meaning slips. A galaxy can be extremely far in today's coordinates, yet its light began in a much smaller universe. The universe does not merely contain distances, it manufactures them over time. Comoving distance is the map coordinate that stays fixed for galaxies riding the expansion. It treats galaxies like pins in a stretching fabric, where the fabric grows but the pins keep their labels. Physical distance changes with time, but comoving distance stays constant if the galaxy has no local motion. This lets us compare early and late times without constantly changing the ruler. Local motion still exists, of course, and gravity complicates the picture. Galaxies and clusters orbit and collide, and nearby groups can fall together despite expansion. Yet on the larger scales, the comoving framework captures what the universe is doing overall. It separates the cosmic flow from the smaller, messier motions inside it. The scale factor, written as a t, is the simplest way to express that stretching. When a t grows, the universe's typical separations grow with it. We do not need the full equations here, only the idea that the cosmic ruler itself evolves. A galaxy's comoving coordinate can remain stable, while its proper distance increases as AT increases. The scale factor also gives us a clean way to translate redshift into how much smaller the universe once was. When we say a galaxy is seen at high redshift, we're saying its light began when AT was a fraction of today's value. That fraction is not just a number, it is a clue to density, temperature, and the pace of cosmic change. Light is stretched by the same expansion, and that stretching is redshift. A photon leaves a galaxy with some wavelength, and it arrives with a longer wavelength. The shift is not mainly because the galaxy is flying through space like a rocket. It is because the space the photon crosses is expanding while it moves. In spectra, the evidence is precise and almost elegant. Familiar atomic lines, hydrogen, oxygen, calcium, appear displaced, like a song transposed into a lower key. The pattern stays intact, but the whole melody slides toward longer wavelengths. That shift is a signature of the universe's growth, written directly into light. Redshift becomes our cosmic ruler because it encodes how much the universe expanded during the photon's journey. Higher redshift means the light was emitted when AT was smaller. Higher redshift means we are looking further back in time. Astronomers use spectra to measure redshift precisely, and then infer distances through a cosmological model. It is not a single-step conversion. and that is part of the drama. You measure a redshift, but to turn it into distance, you must assume a history of expansion. That history is constrained by data, yet it still carries uncertainty, and the universe makes us earn every decimal place. Even so, the agreement between different methods is one reason modern cosmology is so confident. This is where the edge begins to feel like a horizon rather than a wall. A wall is a place you could reach and touch. A horizon is a limit set by travel time and geometry, and it moves with the observer. The cosmic horizon is not a boundary in space alone, it is a boundary in space-time. On screen, a horizon is always personal. Stand on a beach, and the line is centered on you no matter where you walk. The cosmic version is the same, except the shore is time itself. The universe does not end at the horizon. Our access ends there, at least through light. The first horizon to define is the particle horizon. It is the maximum distance from which light could have reached us since the beginning. It marks the radius of the observable universe at the present time. Everything beyond it may exist, but it has not had time to send us information. The particle horizon is the edge of what we can see today. In practice, this horizon is not a sharp border in any telescope image. It is a conceptual sphere around us, drawn by the finite speed of light and the finite age of the cosmos. If a region lies beyond it, then no matter how bright it is, its photons simply have not arrived. In that sense, the particle horizon is a limit on evidence. The second horizon is the event horizon, and it points toward the far future. It is the maximum distance from which light emitted now will ever reach us, even given infinite time. If the universe's expansion continues to accelerate, some regions are already slipping away causally. Their future signals will never arrive, no matter how long we wait. The event horizon is the edge of what we will ever be able to receive. This is where the story turns quietly unsettling. A galaxy can be visible today because its older light is already on the way, and yet it can be destined to vanish from causal contact. Over immense time, the accelerated expansion can stretch space so fast that new photons can never close the gap. The universe does not slam a door. It slowly increases the distance until the door cannot be reached. The third boundary is not exactly a horizon, but it is a useful marker. It is the Hubble sphere, defined by the distance where recession speed equals the speed of light. In an expanding universe, recession speed increases with distance because more space lies between. At the Hubble radius, the expansion rate makes distant galaxies recede at about c. Beyond it, recession exceeds c without violating relativity because it is not local motion. The key phrase is not local. Relativity forbids objects from outrunning light through space in their immediate neighborhood. Expansion is different because it is space itself changing, and the metric can make separations grow faster than c. In your local patch, physics remains ordinary, and light still wins every race. These three ideas are often confused, and the confusion feeds bad metaphors about an edge. The Hubble sphere is not the same as the particle horizon, and it is not the same as the event horizon. Light from beyond the Hubble sphere can still reach us if conditions change over time. The Hubble radius evolves as the expansion rate evolves, and photons can cross it in either direction. A useful way to picture this is to watch a photon's path on an expanding grid. Early on, the grid stretches rapidly and the photon can seem to lose ground. Later, if the expansion rate changes, the photon can begin to gain, and eventually it arrives. The Hubble sphere is a momentary balance point, not a permanent boundary. The particle horizon is about the past, and it is set by the finite age of the universe. The event horizon is about the future, and it is set by the long-term behavior of expansion. The Hubble sphere is about the present expansion rate, and it is a snapshot boundary. Together they define what we can see, what can ever affect us, and what is currently receding faster than light. All of them are edges made of light, not edges made of matter. They do not mark where space ends, they mark where communication ends. They do not imply a center, because every observer has their own horizon. If you lived in another galaxy, your observable sphere would be centered on you. The universe can be vast and uniform while each viewpoint remains bounded. That is a profound kind of humility, because it means no one gets the full map. The cosmos may be far larger than what any observer can access, even in principle. We infer what lies beyond by assuming the same laws continue, and by trusting the patterns we can see. Yet the unseen remains real, whether or not it is reachable. This returns us to the central question, but in a sharper form. If the universe has an edge in any meaningful sense, it is an edge of access. Beyond our horizons may be more space, or different regions, or structures we cannot yet imagine. The unsettling part is that beyond is not blocked by a barrier, it is blocked by time. If time is the gatekeeper, then every observation becomes a negotiation with the past. We are not just looking outward, we are looking backward through a sequence of physical conditions. The farther we go, the denser the universe becomes and the more extreme the environment. At some point, the familiar universe of stars and galaxies has not yet formed. Look back time adds a second layer of tension, because the farthest objects are not just distant. They are younger versions of themselves caught mid-formation. A galaxy at high redshift is not a mature spiral seen far away. It is a rougher, brighter, more chaotic ancestor, still building stars at a furious pace. The visuals here are almost archaeological. You see clumpy star-forming regions instead of graceful arms, and you see irregular shapes that look like collisions frozen mid-splash. Gas is more abundant, and the first generations of massive stars burn hot and short. In those early systems, the universe is still learning how to make galaxies, so when we push telescopes deeper, we are not just hunting faint points, we are approaching the era when galaxies first ignited, when the first heavy elements were forged, and when darkness began to break. The farthest light is not the light from the farthest place, it is the light from the earliest time that can still reach us. That distinction matters, because farthest can mislead the imagination. The edge is not a place where matter piles up, and it is not a rim you could travel toward. It is a time slice, defined by what has had time to send a signal. The universe's geography is inseparable from its history, but there is a limit to how far back ordinary light can show. Early on, the universe was hot enough that electrons and nuclei could not stay bound. Matter existed as a plasma, and photons scattered constantly off free electrons. In that state, the universe was opaque, like a fog that light could not cross. Before a certain time, there was no clear line of sight. Opacity here is not metaphorical. It is a measurable property of a medium. In a plasma, free electrons are efficient scatterers, and photons ricochet like pinballs. Their mean free path is tiny, so they cannot travel in straight lines for long. The universe could be filled with light, and still be visually impenetrable. As expansion cooled the plasma, a transition occurred. Electrons combined with nuclei to form neutral atoms, and photons stopped scattering so frequently. Light decoupled from matter and began to travel freely across the cosmos. That moment is called recombination, and it happened about 380,000 years after the beginning. The light released then is still arriving now, stretched into microwaves. Recombination is a misleadingly gentle word for a dramatic change in visibility. The temperature dropped enough for protons and electrons to bind into hydrogen, and the fog thinned almost everywhere at once. The universe went from opaque to transparent on cosmic timescales, and suddenly, photons could stream across expanding space. That is why the afterglow exists as a coherent signal. That afterglow is the cosmic microwave background, and it is the oldest light we can see directly. It comes from every direction, because it is a shell around us in time. It is not a surface in space like a wall, but it behaves like a horizon. Beyond it, the universe is not empty, but it is hidden from photons. The fog is not distance, it is opacity. If you could see microwaves with your eyes, the sky would glow with a near-uniform light. It would not look like stars. It would look like a faint, all-encompassing backdrop. Tiny variations would appear as subtle mottling, like the grain of a photograph. Those faint patterns are among the most important images ever taken. The microwave background also carries a message about structure. Tiny temperature variations map tiny density variations in the early universe. Those variations grew under gravity into galaxies, clusters, and the web of matter between them. The oldest light is not just a limit, it is evidence, and it anchors the story of how the universe evolved. The variations are small, tens of microkelvin, yet they are enough. Slightly denser regions pull in more matter, and over billions of years they become the scaffolding of the cosmic web. Slightly emptier regions become voids, expanding into vast dark basins between filaments. The universe we see now is, in a sense, the microwave background grown up. Even here, the edge is not absolute in principle, only in practice for light. Other messengers could cross earlier epochs more easily. Neutrinos decoupled earlier than photons and could, in theory, bring us information from a younger universe. Gravitational waves could carry signals from violent processes before recombination. These channels are difficult to detect, but they remind us that horizons depend on what you can measure. That dependence is a subtle, powerful idea. A horizon is not only about the universe, it is also about the observer's tools. As detectors improve, the edge can retreat, not because space changes, but because our access widens. The universe keeps its secrets, yet it also leaves loopholes for those who can listen differently. Still, for most of cosmic history as we observe it, light sets the boundary. It sets the particle horizon for what we can see now. It sets the event horizon for what can ever reach us later. It sets the redshift ladder that turns spectra into distances and times. It sets the feeling that the universe has an edge, even if space itself does not. The expansion that makes these horizons also reshapes intuition about motion. Galaxies can recede faster than light, and yet their local physics remains normal. No object locally outruns a photon in its neighborhood. The faster-than-light recession is a property of the metric, not of engines. This is why the universe can be unbounded, while our view remains finite. In this framework, the observable universe is not a special region chosen by fate. It is simply the region that has had causal contact with us since the beginning. Its radius is large because space expanded while light traveled. Its edge is a horizon because time is limited. Its meaning is not that the cosmos ends, but that our information does. That is a strange kind of edge, an edge that is everywhere around us, and yet nowhere we can point to on a map. It is the boundary between what has had time to speak and what has not. It is also a reminder that the universe is not obligated to be fully knowable from one location. The cosmos may be comprehensible, yet still incomplete in our hands. The suspense builds as we realize what the farthest light represents. Every deeper observation is closer to a time when there were no stars, no galaxies, and no transparent space. The farther we look, the more the universe simplifies into plasma and radiation. The story narrows toward a moment when light itself could not travel freely. The edge becomes a fog bank in time, and yet the fog is not the end of the universe, only the end of our direct sight. Beyond it may be earlier physics, different forms of information, and clues to why expansion behaves as it does. The central question remains open, but the chapter's answer is precise. The first true edge is not a wall you could reach. It is a horizon made of light, drawn by the universe's age and its expansion. Now the question tightens into a chase. If light sets the edge, then the oldest light should mark the boundary of what we can know. We turn from distant galaxies to the faint afterglow behind them, and we ask what happens when we follow it all the way back. We have chased the horizon made of light, and it leads to a final glow that seems to hang at the end of vision. It feels like a surface you could approach, yet it is time itself, compressed into a luminous boundary. The universe is not capped by a rim in space, like a dome over a landscape. Our view is capped by how far photons can travel unimpeded, and by how long the cosmos has had to let them run. In the first hundreds of thousands of years, the cosmos was a hot plasma, brighter than any star and denser than any vacuum we know. Electrons and protons moved freely in a charged sea, and light could not stream in straight lines. Photons scattered constantly off free electrons through Thomson scattering, a simple electromagnetic process with enormous consequences. Their paths were short, jagged, and tangled, so the universe was effectively opaque, more like the interior of a fog bank than open space. In that early era, radiation and matter were tightly coupled, behaving like one mixed fluid rather than separate ingredients. Pressure waves rippled through the plasma as sound, and gravity pulled against them, trying to deepen every slight overdensity. Those waves were not metaphorical. They were real oscillations in density and temperature, driven by radiation pressure pushing outward while gravity tugged inward, and they left a measurable rhythm that still echoes in the sky. Expansion cooled everything, and cooling changed what matter could become, because the rules of chemistry depend on temperature. As the universe expanded, temperature and density dropped together, until atoms could finally hold together without being torn apart by energetic photons. Around 380,000 years after the Big Bang, Recombination began in earnest, and the cosmic plasma started to change its character. Electrons joined protons to form neutral hydrogen across the cosmos, and the electric glare of free charges began to fade. Recombination is not a single instant, but a rapid transition on cosmic timescales, like dawn arriving across a continent. The free electron fraction collapsed, scattering rates fell, and the mean free path of light grew from microscopic to cosmic. As electrons disappeared into atoms, the fog thinned in a way that would look almost magical if we could watch it in real time. Photons stopped ricocheting and began to free stream across expanding space, carrying with them the last imprint of the plasma's conditions. This is decoupling, when light and matter stopped behaving as one fluid and began to evolve separately. The universe became transparent to most electromagnetic wavelengths, and darkness, space between luminous objects, became possible for the first time. The photons released then were not created in one flash, as if the universe struck a match. They are the last scattered photons leaving the plasma from slightly different depths and times, each one departing when it finally found a clear path. Those photons still arrive today, cooled and stretched by expansion, arriving not as visible light but as microwaves. Their wavelengths have grown by a factor of roughly 1,000, a direct record of how much the universe has expanded since that era. We call this relic glow the cosmic microwave background. It is the oldest light we can observe directly with electromagnetic telescopes, a pervasive afterglow that fills every direction even when the sky looks black. Its spectrum is an almost perfect blackbody, the signature of matter and radiation once sharing thermal equilibrium. Today it corresponds to a temperature of about 2.725 Kelvin, only a few degrees above absolute zero, yet spread across the entire sky. That number is not a metaphor, and it is not a guess, and it did not come easily. It is measured across frequencies, and the curve matches thermal equilibrium exquisitely, so precisely that deviations become a tool for checking instruments and models. Visually, the blackbody curve is a smooth hill, rising and falling with frequency in a way that seems almost too clean for nature. When plotted, the residuals hover near zero, as if the early universe left behind a laboratory-grade calibration source. Historically, this glow was not always an obvious prediction, even though the Big Bang framework implied a hot beginning. In the mid-20th century, theorists argued that a cooled remnant should remain, and then, by accident and persistence, it was found. In 1965, Arno Penzias and Robert Wilson struggled with a stubborn hiss in their radio antenna, a noise that would not go away. They cleaned equipment, checked pigeons, and tested every source of interference until the simplest explanation remained. The sky itself was glowing. The CMB is nearly uniform in every direction, a smooth bath of radiation that seems to ignore our local clutter of stars and galaxies. That uniformity tells us the early universe was remarkably smooth on large scales, with temperature differences of only a few parts in 100,000. Yet it is not perfectly smooth, and the imperfections are the point, because they are the universe's first recorded texture. Tiny anisotropies appear at the level of tens of microkelvin, and they form a mottled pattern that looks random until you analyze its statistics. Those microkelvin variations map slight differences in density and gravitational potential, and they are not merely cosmetic. They are the seeds from which later structure grew, the faint blueprint that gravity would spend billions of years turning into architecture. Where the plasma was slightly denser, gravity had a head start, compressing matter a little more efficiently than its surroundings. Over billions of years, those regions gathered matter into galaxies and clusters, building the bright nodes of the cosmic web. Where it was slightly less dense, matter drained away over time, leaving emptier and emptier volumes. Those regions became the vast voids that now separate filaments of the cosmic web, dark basins between luminous strands. So the CMB is a baby picture, but it is also a blueprint, and that dual role is what makes it so powerful. It encodes the initial conditions that shaped everything we later see, while also revealing the physics of the plasma that produced it. We can measure these patterns with extreme precision, and the story of that precision is itself a chapter in scientific ambition. Satellites like COBE, DWMAP and Planck turned faint mottling into a quantitative map, each mission sharpening the image and tightening the error bars. COBE first confirmed the blackbody spectrum and then detected the anisotropies, a discovery that transformed cosmology into precision science. WMAP mapped the full sky with finer resolution, and Planck refined the picture again, revealing subtle features in temperature and polarization. The map looks like a sphere around us, and that is where intuition breaks, because spheres suggest centers. It feels like we are centered inside a cosmic shell, as if the universe arranged its oldest light to frame our location. That feeling is an observational illusion created by light travel time, and by the simple fact that we see in cones of past history. We see the CMB from the same look-back time in every direction, because in every direction we are looking to the moment transparency began. In any direction we look back to the moment the universe became transparent, and that moment defines a last scattering surface in time. It is called a surface because it behaves like one in our data, even though it is really a boundary condition on visibility. It is a photosphere, like the sun's, but stretched across the cosmos and written into the geometry of space-time. The sun's photosphere is a layer in space, where photons last scatter before escaping into space, while the CMB photosphere is a layer in time. That distinction matters because it tells us why the CMB cannot be approached like a distant cloud. It is not a wall you could fly toward and touch, because as you move, your past light cone changes and the boundary moves with you. If you travelled far enough, you would still see it surrounding you, because you would be sampling a different region of the early universe. Every observer in every galaxy sees their own last scattering sphere, and the centre is not special, it is simply wherever you are. That is why the CMB can look like an edge without being one, and why the metaphor of a wall both helps and misleads. It is the boundary of direct sight, not the boundary of existence, and it is drawn by physics rather than by geography. The phrase last scattering surface hides a subtle truth, and that truth shows up when we demand precision. The CMB comes from a finite thickness of time, not an infinitely thin shell, because recombination unfolded over a range of temperatures and densities. Recombination took time as the universe expanded and cooled, and different regions reached neutrality at slightly different moments. Photons last scattered over a range of redshifts, creating a blurred photosphere whose thickness can be modelled and measured. Even so, the signal is sharp enough to function as a cosmic reference screen, a background against which later effects can be detected. It is the earliest electromagnetic snapshot we can cleanly interpret, because earlier light is repeatedly scrambled by scattering. This is where the chapter's tension tightens. We can map this screen with exquisite precision, yet what lies behind it stays veiled, as if the universe has drawn a curtain exactly where our curiosity becomes most urgent. Behind the CMB, the universe is not empty, and it is not silent, but it is opaque to electromagnetic light. Photons could not travel freely then, so any image-like information is erased by countless scatterings, the way a face disappears in thick fog. If we ask what happened earlier, ordinary telescopes cannot answer, no matter how large we build them or how long we integrate. The information is trapped in a plasma era that light cannot cross, because the medium itself destroys directional memory. The wall is not made of matter piled at the edge of space, and it is not a physical barrier you could collide with. The wall is made of scattering, a limit on how far photons can carry images, and it is imposed by the density of free electrons. That limit is why the CMB feels like the last light, and why its discovery felt like finding a message in a bottle. It is the oldest message that can travel to us without being erased, a fossil signal that survived the universe's first great transition. But the universe has other messengers, and they do not all scatter the same way, which opens a narrow door beyond the curtain. Some can slip through epochs that trap photons, carrying information from earlier times in forms that are harder to detect. Neutrinos are one candidate messenger, produced abundantly in the early universe, and barely interacting with matter. They interact weakly, so they decouple far earlier than photons, when the universe was seconds old and nuclear reactions were still setting primordial abundances. A cosmic neutrino background should exist, older than the CMB, filling space with relic particles that have been cooling ever since. Detecting it directly is extraordinarily hard, because the neutrinos are cold and elusive, and their interactions are too rare for easy capture. Gravitational waves are another candidate messenger, and in some ways they are even more indifferent to matter than neutrinos. They interact extremely weakly with the plasma, and they can cross the early universe almost untouched, carrying information as distortions of spacetime itself. If inflation happened, it could have produced primordial gravitational waves, stretching quantum fluctuations to cosmic scales. Their imprint might survive as a specific pattern in CMB polarization, Linking the afterglow we see to physics at energies far beyond any accelerator. That pattern is called B-mode polarization, and it is a target of intense searches because it would be a rare, clean signature. Dust and foregrounds can mimic it, so the measurement is delicate, requiring careful subtraction and multiple frequencies to separate sky from contamination. Even without primordial waves, later processes generate gravitational wave backgrounds that add complexity to the cosmic hum. Merging black holes and early-phase transitions could leave a broad spectrum across spacetime, a faint chorus that future detectors may learn to isolate. These messengers widen the story beyond light, while keeping the same central theme of horizons and limits. They suggest the CMB is not the end of the universe, only the end of one channel, and that other channels may carry older, subtler records. Still, for now, the CMB remains our cleanest boundary, and its cleanliness is part of its authority. It is the farthest back we can see with confidence, using electromagnetic radiation, and it provides a stable reference frame for testing cosmological models. The CMB also functions as a ruler for cosmology, because its anisotropy spectrum contains acoustic peaks, frozen echoes of sound waves in the early plasma. Those peaks arise because some modes were caught at maximum compression, while others were caught at maximum rarefaction when photons finally escaped. The physics behind the peaks is straightforward in plain terms. Gravity tries to clump matter, and radiation pressure resists, creating oscillations. In more formal terms, it is a set of coupled perturbation equations whose solutions leave a harmonic series in angular power. Those peaks encode the universe's composition and geometry, and they do it with surprising redundancy. They tell us about baryons, dark matter, and dark energy through their relative heights and positions, and they constrain the expansion rate through how distances project onto angles. They also let us test spatial curvature, a question that sounds philosophical until you realize it is measurable. In a flat universe, the characteristic angular scale of the first peak lands where we observe it, because light rays and triangles behave in the Euclidean way on large scales. The data so far indicate near flatness, within tight error bars, which is both satisfying and unsettling. Near flat does not settle the question of total size, but it narrows the options, pushing many exotic geometries into smaller and smaller corners of parameter space. A universe can be flat and infinite, extending without bound, with new regions continuing beyond any horizon we can ever reach. A universe can also be flat and finite, if space wraps around with a non-trivial topology, so that travelling far enough could, in principle, bring you back. Curved spaces add more possibilities, and their analogies help even when the reality is higher dimensional. Positive curvature can imply a finite volume without an edge, like a three-dimensional analogue of a sphere's surface, while negative curvature suggests an open geometry that is often infinite. The CMB patterns help constrain which global shapes remain plausible, because curvature changes how physical scales appear on the sky, yet the CMB is still only our patch's screen, showing the observable universe's boundary in time, not the full extent of reality. This is the uneasy balance of modern cosmology, where certainty and ignorance sit side by side in the same dataset. We have a precise map of the afterglow and a limited view of what preceded it, and we must be honest about which claims come from which kind of evidence. We can infer earlier conditions indirectly, through nucleosynthesis and expansion history, and through the way perturbations evolve forward in time. But inference is not the same as direct sight, and the difference matters when we ask what is fundamental versus what is merely consistent. The CMB therefore deepens the central question rather than closing it, because it defines a boundary with mathematical clarity. If the universe has an edge in any meaningful sense, it is a horizon of information, a limit on what can be known by signals travelling at finite speed. Beyond that horizon may be more of the same cosmos, continuing smoothly, with the same laws and similar statistics. Beyond it may be regions with different initial conditions or even other universes, and the CMB cannot confirm or deny them, because it is not a window into that domain. Or beyond it may be a regime where space-time itself is emergent, and where our classical notions of distance and time are approximations. The CMB does not tell us what is beyond, it tells us where our vision fails, and failure can be as informative as success. The failure is not a defect of instruments alone, and it is not something we can fix by building a bigger dish. It is a physical limit set by the universe's early opacity to electromagnetic radiation, a property of the medium that existed before atoms formed. so the wall that isn't a wall becomes our most important clue, because it is both barrier and artifact. It is a boundary that moves with the observer, and it is drawn in time, which means it is universal without being absolute in space. We can stand anywhere and still be surrounded by it, and that fact quietly undermines the idea of a single cosmic center. Yet it also tempts us to treat the CMB as a literal surface, because surfaces can be measured, compared, and turned into numbers that models must match. We measure its temperature, its spectrum, and its polarization, and we do it across the whole sky with careful control of systematic errors. We measure its anisotropies and convert them into parameters that describe our cosmic history, densities, expansion rates, and the amplitude of primordial fluctuations. The more precisely we measure, the more we notice what is missing and what must be explained. The CMB is smooth enough to be startling and structured enough to be decisive, which is a rare combination in nature and a gift to theory. It tells us the universe began hot and dense, and then expanded and cooled, and it tells us that this is not a poetic origin story. It tells us the seeds of structure were present very early, and that those seeds were small enough to require extraordinary early uniformity. It does not tell us why those seeds had the pattern they did, or why the initial fluctuations had the amplitudes we infer. It does not tell us what set the initial conditions or what came before, and that silence is part of the mystery that keeps the horizon sharp. That gap is the chapter's mystery, and it is not a trivial one, because it points to physics we have not yet tested directly. We can read the universe at 380,000 years old, but the earlier pages are sealed behind scattering, and the ink is written in messengers we barely know how to catch. So we end with a boundary that looks like a wall and acts like a screen, hovering behind every galaxy like a private backdrop. It is the last light we can see, and it is not the end because the universe continues beyond our electromagnetic reach. If the CMB is a time wall, then its patterns are a code, and codes invite interpretation. The next question is whether that code reveals the universe's true shape and size, or whether it only hints at them through statistical shadows. We leave the afterglow behind as an object of awe and treat it as evidence, because wonder alone cannot do the accounting. We turn from the wall that isn't a wall to the geometry it implies, and we ask what a sphere of ancient light can say about the whole stage. If an edge is really a horizon, then the only way beyond is inference, and inference must be disciplined. We will ask what the CMB can tell us about the whole cosmos, and what it cannot, even when our maps become sharper and our models more elegant. Now the chase changes form, because the horizon is no longer a line we approach, but a dataset we interrogate. We cannot see past the photosphere, but we can read the ripples on it and try to reconstruct the room that produced them. The central question returns with sharper teeth, because the CMB makes the limit feel both intimate and absolute. If there is no known edge to space, why do horizons keep fencing our knowledge? And what does it mean that the fence is made of time? Beyond the fence may be more universe, other universes, or deeper rules that make our categories feel provisional. The afterglow does not answer, but it sets the stage for the next test, and it reminds us that the universe's oldest light is also its most careful silence. The last light gave us a screen, not a wall. Now we ask what the screen implies about the stage itself. At the top of the sky, where the daytime blue thins into a cold, ink-black dome, you might think you've reached the edge of everything. The stars sharpen, the air darkens, and the mind instinctively searches for a rim, some final border where reality stops. But the deeper truth is more unsettling. Space offers no obvious boundary to point at, yet our intuition keeps trying to turn far away into outside. We are creatures shaped by rooms and coastlines, so we imagine the cosmos the same way. The central question stays the same, even as the language gets slippery. If the universe has an edge in any meaningful sense, what lies beyond it? More space, nothing at all, other universes, or rules we cannot yet name. To chase an edge, we first need a definition of space that physics can test, rather than poetry can suggest. Geometry is that definition, because geometry tells matter and light how to move, and it tells rulers how to measure. In everyday life, geometry feels fixed and flat, like a grid drawn across the world. Floors look level, parallel lines seem to never meet, and triangles add up the way we learned in school. Cosmology begins by admitting that this comfort may be local, like calm weather in a single valley. On the larger scales, space can be curved, and curvature can imitate an edge without ever producing a boundary. Curvature is not a bend into some external direction, as if space were a sheet floating in a larger room. It is an internal property of distances and angles measured within the space itself, something you can detect without stepping outside. A simple way to feel that difference is to imagine surveying, not sculpting. You do not need to see the whole landscape, you only need to measure how paths and angles behave as your triangle grows. Start with the simplest diagnostic. Draw a triangle and add its angles, then compare the sum to 180 degrees. In flat geometry, the sum is 180 degrees no matter how large the triangle is, whether it spans a tabletop or a continent. In curved geometry, the sum changes with size, and the deviation becomes a measurable signature. On a positively curved surface, like a sphere's skin, triangle angles add to more than 180 degrees. Great circles that start parallel can meet, the way lines of longitude converge at the poles. On a negatively curved surface, like a saddle, triangle angles add to less than 180 degrees. Lines that start parallel can diverge, as if the space between them is being stretched from within. Parallel lines are the second diagnostic, because they expose curvature without needing a protractor. In flat space, true parallels stay separated forever, keeping a constant distance as they run onward. In positive curvature, there are no global parallels in the Euclidean sense, because straight paths eventually turn toward one another. In negative curvature, there are many, and they spread apart faster than intuition expects. These tests are not classroom tricks, and they are not limited to two-dimensional cartoons. They are the same logic used to infer the universe's large-scale geometry from observable patterns, where light itself acts as our measuring tape. Historically, this was a radical shift in what geometry meant. For centuries, Euclid's rules felt like pure truth, until mathematicians like Gauss, Bolyai, and Lobachevsky showed that consistent non-Euclidean geometries were possible. That mathematical freedom set the stage for physics to make a bolder claim. Space is not required to be Euclidean, and the universe does not owe our instincts any loyalty. General relativity makes the bridge from intuition to cosmos, and it does so with a startling economy. Mass and energy curve spacetime, and curved spacetime guides the paths of matter and light. In Einstein's picture, gravity is not a force pulling across empty space like an invisible rope. Gravity is geometry, and freefall is motion along the straightest possible paths. Geodesics traced through curved spacetime. That idea scales up to the whole universe, where the straightest path becomes a cosmic rule for how light travels between galaxies. If the cosmos is homogeneous and isotropic on large scales, its geometry fits a small family of possibilities. The Friedman, Lemaitre, Robertson Walker models describe that family, and they do it with remarkable restraint. They allow flat, open and closed spatial geometries, each tied to a particular sign of curvature. Flat means zero spatial curvature in the average sense, like a plane that extends without bending. Open usually means negative curvature, where space has a saddle-like character on large scales. Closed usually means positive curvature and finite volume, like a higher dimensional analogue of a sphere. Curvature also affects how expansion behaves, but it is not the same thing as expansion. Space can expand whether it is flat, open or closed, because expansion describes how distances change with time, not how triangles add. The key parameter is OK, the curvature density parameter, and it is deceptively compact. It encodes how far the universe is from perfectly flat geometry, comparing the actual cosmic energy budget to the critical value that yields flatness. If OAK is 0, the spatial slices are flat in the standard model, at least within our measurement precision. If OK is positive or negative, the geometry is curved accordingly, and that curvature alters how light beams converge or diverge. The cosmic microwave background gives the cleanest curvature test we have, because it is both ancient and statistically rich. Its acoustic peak scale acts like a standard ruler projected onto the sky, an imprint of sound waves in the early plasma. Long before atoms formed, the universe was a hot charged fog where photons scattered constantly off electrons. Tiny density ripples drove pressure waves, and those waves froze into a pattern when the universe cooled enough for neutral atoms to form. That moment, recombination, released the CMB, a nearly uniform glow that now arrives as microwaves after 13.8 billion years of redshifting. The angular size of its characteristic features tells us how space has shaped the journey of that light. If space is positively curved, light paths converge and the ruler looks larger on the sky, as though the sky were wrapped around us. If space is negatively curved, light paths diverge and the ruler looks smaller, as though the sky were stretched open. Planck and other datasets place OK very close to zero, tightening the error bars until curvature becomes a whisper. Large-scale structure and baryon acoustic oscillations support the same near-flat conclusion, using galaxies as a later-time echo of the same physics. Near-flatness is a powerful constraint, but it is not a final answer about size, and the distinction matters. A universe can be extremely large yet still measurably curved only weakly, the way Earth looks flat from the ground. Near-flatness also does not guarantee infinity, even though the words feel connected in everyday speech. Flatness is about local geometry, while infinity is about global extent, about whether the space goes on without end. This is where the story changes from curvature to topology. Topology asks how space is connected, not how it is bent. Two spaces can have the same local curvature and still differ globally, like two maps drawn with the same scale but different edge rules. Locally, they can look identical under a microscope, while globally they can wrap, repeat, or identify distant points. Topology is the hidden rulebook for whether travel can loop, and it is indifferent to our sense of direction. It decides whether the universe can be finite without any edge to fall off, and it does so by changing what going straight ultimately means. A finite object without an edge sounds impossible, because we picture borders as walls or cliffs. The trick is to stop thinking in terms of embedding. Stop imagining space as an object sitting inside a larger container. Use the two-dimensional analogy that does not require extra physics. Ants on a sphere's surface can walk forever and never find an edge. The surface area is finite, yet the surface is unbounded, and that pairing is the key. There is no boundary line where the surface stops, only a closed path that eventually brings you back home. That is the core idea we need in 3 dimensions, even though it strains the imagination. Our space could be finite in volume, yet unbounded, if its topology closes on itself in a way that has no boundary. The simplest flat example is the 3 torus, a shape built from identification rather than curvature. Imagine a cube where exiting one face makes you re-enter from the opposite face, as if the universe were tiled seamlessly. In that space, straight motion continues without obstruction, and inertia never notices the trick. Travel far enough in one direction and you return, not because you turned, but because space quietly identifies points that look separate in the cube picture. The geometry can remain flat everywhere, with zero curvature, while the topology is non-trivial, and that is the subtlety. Flat does not mean infinite, it means locally Euclidean, like a neighborhood that never reveals the city's full layout. Closed positive curvature spaces offer another route to finiteness, and they feel more intuitive at first glance. A 3-sphere is the 3-dimensional analogue of a sphere's surface, with finite volume and no edge, even though it cannot be visualized directly. Open negative curvature spaces are often infinite, but topology can complicate that too, and the complication is not mere wordplay. Some negatively curved spaces can still be finite if they are compactified, meaning their points are identified in a repeating pattern. The point is not to list every manifold, and it is not to turn the cosmos into a catalogue of exotic shapes. The point is to break the reflex that finiteness implies a boundary, because that reflex is where the illusion of an edge begins. This reframes the central question in a sharper way, with less romance and more precision. If the universe feels like it has an edge, maybe the feeling comes from our assumptions about what finite must look like. An edge is a boundary where space ends and something else begins, like a shoreline against an ocean of nothing. A wrapped space has no such boundary, only repetition and return, an ending that is really a loop. That possibility creates narrative tension. The beyond we chase might not be outside the universe but elsewhere within it. If space wraps, the edge could be a loop, and the loop could be enormous. You could travel forever, never hit a wall, and still come back to where you started, arriving from a direction that feels impossible. But a wrapped universe would not hide perfectly, because physics is stingy with secrets. Repetition would leave fingerprints in what we observe, because light would have multiple paths to reach us, like echoes in a vast dark cathedral. In a small enough wrapped cosmos, we might see the same galaxy in different directions at different ages, because the light took different length routes. the sky would contain duplicates, subtly warped by gravitational lensing and by the time delay between paths. The cleanest test uses the CMB because it is a nearly uniform screen at a known distance in time. If space repeats, the last scattering surface can intersect itself, and that intersection is not metaphorical, it is geometric. Those self-intersections would appear as matched circles in the sky, a signature as crisp as a fingerprint if the topology is small enough. Two circles in different directions would share the same temperature fluctuation pattern, point for point, because they are the same physical ring seen twice. The logic is geometric and strict, which is why it is so compelling. If the same physical patch of the CMB is seen along two paths, the anisotropy pattern must match along the corresponding circles, aside from noise and foreground contamination. Teams have searched for these matched circles in WMAP and Planck data, pushing algorithms across masked skies and imperfect maps. The search is challenging because noise, foregrounds and masking reduce sensitivity, and because our own galaxy paints bright microwave structures across the view. So far, no convincing matched circle signal has been found, and that absence is informative. That rules out many small topologies, where the fundamental domain would be smaller than the observable universe, because such a universe would almost certainly reveal repeated circles. But it does not rule out all topologies, and it does not end the story. A wrapped universe could be larger than our observable volume, making repeats too subtle, too partial, or too distant to detect with current resolution. Some topologies also produce weaker or more complex signatures than simple circle matching, especially when the identification scales differ by direction. The absence of evidence is a constraint, not a closure, and cosmology has learned to respect that difference. We have also looked for other hints, because topology can influence statistics even when it hides direct repetition. Topology can suppress large-angle CMB correlations or introduce preferred directions, though cosmic variance limits certainty on the very largest scales. Large-scale structure offers another avenue, because repeating patterns could appear in galaxy distributions like a faint watermark, but nonlinear evolution and incomplete surveys complicate the search, since gravity reshapes patterns over time, and our catalogues remain patchy and biased. The observational message is cautious, and caution here is not weakness but discipline. We can say the universe is near flat and lacks obvious small-scale wraparound signatures in current data, which already eliminates many simple possibilities. We cannot yet say the universe is infinite, because infinity is not something you can confirm by looking a finite distance. We also cannot yet say it is finite, because finiteness can hide beyond our horizons, and horizons are built into the rules of light. This is the conceptual bridge from earlier chapters, and it is a bridge made of limitations. The horizon made of light limits what we can see, and topology determines what exists beyond what we can see, whether that beyond is new territory or a return. If the universe is finite and unbounded, the word beyond changes meaning in a quiet but profound way. Beyond the horizon may be more of the same space, possibly repeating, possibly not, but still governed by the same geometry. If the universe is infinite, beyond the horizon is still more space, but never repeating in a global sense, and never closing back on itself. Either way, the horizon is not an edge of existence, only an edge of access. Curvature and topology also change how we imagine a center, and the change is emotionally jarring. A closed universe can be finite without having a central point, because every location is equivalent under the symmetries that define the large-scale cosmos. That equivalence echoes the CMB lesson, which is easy to state and hard to truly feel. Every observer sees themselves at the center of their observable sphere, even when the universe has no special center, because the sphere is drawn by light travel time. So the illusion of an edge has two sources, and they reinforce each other in the mind. One is causal, because light and time limit access. The other is geometric, because our intuition assumes boundaries whenever we hear the word finite. We can now state the tension cleanly, without softening it for comfort. The universe may have no edge at all, and yet it can still be finite, and our data can still be trapped inside a horizon. That tension is not philosophical decoration, and it is not just a word game about definitions. It changes what we mean by outside, and it changes what we mean by the end of space, because end may be a property of knowledge rather than a property of reality. Even if space wraps, there is still a practical boundary, and it is one we can calculate. Expansion can create an event horizon that makes distant regions unreachable, even in principle. because the space between us and them grows too quickly. A wrapped universe could be globally small enough to loop, yet still expanding fast enough that signals fail to complete the circuit. Topology would exist, but communication would be cut, an elegant shape rendered irrelevant by the universe's timing. In an accelerating universe, the event horizon grows into a permanent limit, and permanence changes the emotional weight of distance. More galaxies slip beyond it, and their light becomes redder and fainter until it disappears, leaving behind a quieter sky. This fading is not sudden, and it is not dramatic like a curtain drop, but it is relentless. Wavelengths stretch, photons arrive less often, and the visible universe slowly thins, as if the cosmos were erasing its own distant history. So the next question is not only what space is, but what time allows. The geometry can be closed without edges, while the future still fences us in, turning a universe without walls into a universe with limits. We end where the hook began, with the feeling of a boundary in a universe without walls. The boundary may be an illusion of geometry, or a limit of causality, or both, two different kinds of closure layered on top of each other. There is no known edge to space, only horizons that fence in what light, matter, and information can ever reach. Beyond those horizons may lie more cosmos, other universes, or deeper rules from which space-time itself emerges. Now the chase shifts again. Even if the universe has no edge, expansion can still build a darkness that behaves like one, and it deepens with time. The last light gave us a screen, not a wall, and it taught us to picture limits without imagining stone. Now time itself starts building a different boundary, one drawn not on a map, but inside the future. For most of the 20th century, expansion sounded like a slow coasting after the Big Bang, a momentum gradually spent. Gravity should tug on that motion, so the rate should gradually decelerate, because every galaxy's mass adds to the cosmic pull. That expectation was not aesthetic, and it was not merely tradition handed down from early cosmologists. It followed from general relativity applied to a universe filled with matter and radiation, where the stress, energy content determines how space-time bends and evolves. In the simplest Friedmann-Lemaitre models, the scale factor grows but its growth rate slows because density makes curvature bite. Even without any edge in space, the equations predict an edge in behavior, a steady loss of expansion speed as the cosmos ages. By the 1990s, the question became measurable, and the measurement demanded a light source with disciplined physics. In the late 1990s, two teams tested that expectation using Type Ia supernovae, hunting for a distance marker deep enough to read the expansion history. Type Ia supernovae matter because they are close to standard candles and because their mechanism is comparatively uniform across the sky. A white dwarf in a binary system approaches a critical mass, ignites runaway fusion, and reaches a repeatable peak brightness as it unbinds. In many models, the trigger happens near the Chandrasekhar limit, around 1.4 solar masses, where electron degeneracy pressure can no longer stabilize the star. Carbon and oxygen fuse explosively, and a thermonuclear flame races outward, turning a compact star into an expanding shell of incandescent debris. Repeatable does not mean identical, and the universe rarely gives a perfect laboratory instrument. The light curve shape correlates with intrinsic luminosity, so calibration turns messy explosions into usable rulers, with brighter events fading more slowly and dimmer ones declining faster. That correlation is not magic, and it is not purely empirical luck. It reflects how much nickel-56 is produced in the blast, because radioactive decay powers the glow, and more nickel means a brighter peak and a longer, warmer afterglow. Once calibrated, brightness becomes distance because flux falls with the square of distance, and the geometry is unforgiving. Spectral redshift becomes a measure of how much the scale factor has stretched, because each photon's wavelength is pulled longer as it rides the expanding metric. Distance and redshift together form a time series of the universe's expansion, like a film assembled from still frames. Each supernova is a time-stamped beacon from a different era, because we see it not where it is now, but where it was when the light began. On screen, the data become a scatter of points, faint sparks plotted against their redshifts. Then a curve emerges from the noise. The surprise was consistent across samples and methods, and it landed with the force of a quiet contradiction. Distant supernovae were dimmer than expected in a decelerating universe, implying they were farther away than the old curve allowed. Farther away at a given redshift means the expansion has sped up during the light's travel, so the universe did not merely expand, it accelerated. This was not a claim made lightly, because systematics could fake dimming, and cosmology has learned caution the hard way. Dust, evolution, selection, bias, and calibration errors all had to be confronted, because any one of them could tilt the distance ladder. Dust is especially treacherous because it can hide in host galaxies and in the intergalactic medium, reddening light while stealing photons. Teams checked colours, host galaxies, and light curve corrections, and the signal persisted, even when they modelled extinction and tested different populations. Selection effects were another trap because surveys preferentially find brighter events at greater distances, and that can distort a sample. The teams used careful search strategies and statistical corrections, comparing nearby and distant supernova, and the acceleration signature remained stubbornly present. Later, independent probes reinforced the same conclusion, and they did so with very different physics. Baryon acoustic oscillations provided a standard ruler in galaxy clustering, while the CMB anchored early universe parameters, and together they favoured acceleration with a consistent cosmic budget. The bow feature is a fossil sound wave, a preferred separation scale imprinted when the early universe was hot plasma. When we map galaxies today, that scale appears as a subtle bump in correlations, an echo that lets distance be inferred without supernova light. The CMB adds a second anchor because its temperature fluctuations encode the geometry and composition of the young universe. When those early parameters are evolved forward, the late-time distances only fit if something counteracts gravity's braking, and the simplest name for it is dark energy. So the story of the edge shifts from geometry to dynamics. Space may have no wall, yet the expansion rate can still create a deadline, and the deadline is written into what signals can ever do. To explain acceleration, cosmology adds a component with negative effective pressure, a phrase that sounds abstract until it is translated. In general relativity, pressure gravitates, and negative pressure can drive repulsion, because the combination of density and pressure determines the sign of cosmic acceleration. In the acceleration equation, it is not only mass energy that matters, but also 3 times the pressure term, and that factor changes everything. A sufficiently negative pressure makes the right-hand side flip, so expansion speeds up even while space remains smooth and empty-looking. The simplest form is Einstein's cosmological constant, L, first introduced as a mathematical term and later revived as a physical one. It behaves like a constant energy density of empty space, the same everywhere and every when, so it does not clump into galaxies or dilute with expansion. In the Friedmann equations, L does not dilute as the universe expands, and that is the crucial asymmetry. Matter thins out as volume grows, radiation thins faster because photons also redshift, but L stays put, quiet, persistent, and eventually dominant. As the universe grows, the balance shifts, and what once was negligible becomes decisive. Eventually L dominates the energy budget, and acceleration becomes the default behaviour, because the component that refuses to thin out will always win a long game. But L is also a provocation, because quantum field theory predicts vacuum energy wildly larger than observed, as if empty space should weigh like a star. The measured value is tiny, yet not zero, and that combination is what makes the puzzle feel like a clue. That mismatch is the cosmological constant problem, and it is not a small discrepancy. Naive estimates overshoot by many orders of magnitude, hinting that our accounting of vacuum, gravity, or both is incomplete, or that cancellations occur for reasons we do not yet understand. An alternative is dynamical dark energy, often modelled as a slowly evolving field that changes its energy density over time. Its density changes with time, so the acceleration history can differ from L, and the future boundary can drift rather than settle. In visual terms, L is a flat line, while a field can curve, and the curve matters because it changes the horizon's shape. If the field rolls down a potential, its pressure and density evolve, and the universe's long-term fate becomes a measurement problem rather than a foregone conclusion. To compare possibilities, cosmologists use the equation of state parameter, W, a compact symbol with heavy consequences. It links pressure P to energy density R through P equals W times R, so one number summarizes how the component responds as space stretches. For ordinary matter, W is near zero, because cold matter has negligible pressure compared with its energy density. For radiation, W is 1/3 because photons push as they stream, and their pressure is tied directly to their energy. For a cosmological constant, W is exactly -1, meaning the pressure is negative and equal in magnitude to the energy density. That specific value makes the density constant in time, and it makes the expansion approach an exponential form. If W is greater than -1 but still below -1/3, expansion accelerates but may evolve, and the rate of acceleration can change. If W changes with time, the future boundary shifts, and the event horizon may grow or shrink depending on the trajectory. If W is less than -1, the field is phantom-like in effective behavior, even if the underlying physics is debated. Its density grows as space expands, and the acceleration can become catastrophic because the repulsive component strengthens as the universe gets larger. Measuring W is therefore not a detail, and it is not an academic preference between models. It decides whether the universe approaches a steady descent of fate or races toward a more violent ending, and it decides how quickly the reachable cosmos contracts. Observations so far keep the close to -1, and that closeness is itself a kind of mystery. Uncertainty remains, and small deviations could still matter over cosmic time, because even gentle differences compound across tens of billions of years. This is where the chapter's tension tightens, because the edge we're chasing is not a cliff in space. Dark energy does not draw a physical edge, yet it can erase contact with the rest of the cosmos, and it can do so while the universe still looks calm. To see how, we return to horizons, but now the horizon is about the future rather than the past. The particle horizon limits what we can see, because it is set by the universe's age and light speed, while the event horizon limits what we can ever reach. In an accelerating universe, there exists a cosmic event horizon, and it is as real as any boundary in space-time diagrams. Beyond it, signals we send now will never arrive, no matter how long we wait, because the expansion outruns the message. This is not because light slows down, and it is not because physics changes locally in some distant region. It is because the intervening space expands so quickly that the signal cannot make net progress, as if the road lengthens faster than the traveller can run. The Hubble sphere is not the same thing, even though it sounds similar and is often confused for a horizon. Recession speed equals c at the Hubble radius, but the boundary can move and be crossed, because recession is not motion through space but of space. A photon emitted beyond the Hubble radius can still reach us if the Hubble radius grows with time, which it can in decelerating eras. The event horizon is stricter, and it does not care about a momentary crossing, because it is defined by the entire future history. It is a causal boundary in space-time, defined by the integral of expansion into the infinite future, and that definition is merciless. If the integral converges, there is a finite distance beyond which today's light can never influence, and beyond which tomorrow's light cannot return. As acceleration persists, more galaxies cross that boundary, and the crossing is not dramatic in any local sense. Their last photons still reach us for a while, but each new wave crest arrives more stretched, and the cadence of arrival thins like a heartbeat slowing. Redshift becomes a slow suffocation of information, because every physical scale in the light is diluted. Wavelengths lengthen, arrival rates drop, and distant structures fade into undetectability, not because they vanish, but because their signals become too cold and too sparse. On screen, galaxies that once showed spiral arms and bright cores soften into featureless smudges, then into nothing at all. The universe turns into an archipelago, where each gravitationally bound group remains, while other islands drift beyond any future bridge. Cosmic loneliness is not a metaphor for mood, and it is not a poetic exaggeration for a cold night sky. It is a physical consequence of accelerated expansion and finite signal speed, and it is encoded in the geometry of our future light cone. Even if the universe is spatially infinite, our accessible region becomes effectively finite, and that finitude is operational. The edge is not a place we could visit. It is a limit on interaction, a boundary that tells us where cause and effect can no longer trade messages. This reframes the central question, because edge becomes less about where space ends and more about where influence ends. If the universe has an edge in any meaningful sense, it may be the boundary of what can ever be contacted, even in principle. Dark energy therefore changes what it means to ask what lies beyond, and it changes the emotional temperature of the question. Beyond the horizon may be full of galaxies, yet forever outside our causal reach, like a library whose books are visible through glass but cannot be opened. The loss is not only travel, and it is not only the romance of unreachable destinations, it is knowledge, because astronomy depends on incoming signals, and the future sky can become poorer in evidence, with fewer external checks on our theories. In the far future of a L-dominated universe, expansion approaches de sitter behavior, a steady state of acceleration in a mathematical sense. The scale factor grows exponentially, and the event horizon becomes nearly constant, setting a fixed limit to how far light emitted now can ever go. Stars still burn out, gas is used up, and stellar nurseries run dry as galaxies exhaust their cold fuel. The long-term trend is heat death, a thinning of usable energy gradients, where the universe does not end with a bang but with a fading of opportunities. In that scenario, local structures remain bound, because gravity wins on small scales where densities are high. The local group merges, while other clusters slip away, leaving an emptier observational universe, and the night sky gradually loses its deep background of external galaxies. The CMB also changes in meaning, because its photons continue to redshift and their energy continues to drain. Its photons redshift to longer wavelengths, eventually becoming undetectable against any realistic noise floor, and the once bright afterglow becomes a whisper below the reach of instruments. Future observers could lose the evidence for the Big Bang, and that is not a philosophical claim but a practical one. Without the CMB and without distant galaxies, cosmology becomes harder, even if the universe's history remains true because the sky stops advertising its origin. That is a second kind of edge, and it is subtler than an event horizon. It is an epistemic horizon created by dynamics, where the universe hides its own origin from late-time witnesses, and where the best clues are locked behind redshift and distance. If W is less than -1, the fate can be a big rip, and the phrase is not merely sensational. Acceleration strengthens with time, and the horizon shrinks until even bound systems are torn apart, because the repulsive expansion overwhelms every binding force in sequence. First, clusters unbind, then galaxies, then solar systems, then planets, and eventually atoms, as tidal-like effects of expansion grow without bound. The timeline depends on how far below -1W truly is, and on whether that value remains stable as the universe evolves. The Big Rip is extreme, but it is a clean demonstration of what negative pressure can do when it becomes dominant. It turns expansion from background behavior into a force that defeats all binding, and it transforms the idea of edge into a literal end of structure. A different reversal is also possible if dark energy evolves, and the equations allow more than one ending. If it decays, changes sign, or couples to other components, acceleration could end, and the horizon could loosen rather than tighten. If the energy budget shifts back toward matter or toward a negative effective L, expansion could slow, and the future light cone would open wider. In some models, it could halt and reverse, turning the outward flow into a contraction that gathers everything back. That reversal leads to a big crunch, a collapse where densities rise and temperatures climb, and where the universe's large-scale smoothness is erased. It would be a different kind of edge, a final boundary in time where the question is not what lies beyond but what survives the return. None of these fates are chosen by storytelling, and none are selected for drama alone. They are consequences of the same parameter we are trying to measure, and of whether dark energy is constant, evolving, or something even stranger in disguise. So we live with a strange asymmetry that is easy to miss in everyday intuition. The past horizon is set by the universe's age. The future horizon is set by the universe's acceleration, and those two limits do not mirror each other. The edge that approaches is therefore a deadline, and it advances even if we stand still. Every passing billion years reduces the set of places we can ever influence or learn from, because more world lines slip beyond the boundary where messages can matter. This connects back to the earlier chapter's lesson about walls that move with us, and about limits that are not fixed in space. The CMB screen recedes as we travel. The event horizon closes as time advances, and the closing is written into the expansion history. It also sharpens the hook that began this series, because the cosmos can feel bounded without a rim. At the top of the sky there is no edge you can point to, yet the universe still feels constrained, as if the future itself were narrowing. Now we can name one reason, and the name is not mystical. The boundary is written into the future light cone, and dark energy tightens it, turning the geometry of space-time into a limit on what can ever be shared. We can still ask what lies beyond, but the question changes temperature and it becomes more urgent. Beyond may not be unreachable because of distance alone. It may be unreachable because of time, because the window for contact can close even as the universe continues. This is why measuring dark energy is not optional, and why precision cosmology became a central project. It decides whether the universe's ultimate edge is calm isolation, violent tearing, or eventual collapse, and it decides whether our cosmic neighborhood becomes a lonely island or a temporary harbor. The next step is to ask whether acceleration is fundamental or emergent, and whether it is a property of space-time itself. If it is a field, where did it come from, and why does it have this value, rather than any of the many values that theory seems to permit? To answer that, we have to look backward, not forward, because the deepest clues often live in the earliest conditions. We have to revisit the beginning, when expansion may have been even more extreme, and when horizons were not just consequences but active sculptors of what followed. Transition. To understand whether today's acceleration is a new law, we must ask what happened at the beginning, when the universe may have inflated, and the central question returns with new pressure, because the earliest moments set the rules for everything that comes later. If horizons define our edges, then the earliest horizon may hold the deepest clues about what lies beyond space, and about why our observable universe looks the way it does. To understand whether today's acceleration is a new law, we must ask what happened at the beginning, when the universe may have inflated. The last light gave us a screen, not a wall, and inflation asks what shaped that screen before it ever formed. The CMB is a snapshot of a cooling plasma, yet it also functions like a boundary of knowledge, an apparent limit that invites a deeper origin story. In the 1960s, when the CMB was first detected, it quickly became a kind of cosmic backlight. It illuminated the Big Bang model, but it also highlighted puzzles that were oddly geometric and oddly precise. Inflation enters that gap, reaching behind the CMB time barrier and rewriting what before can mean. Inflation is not a decorative add-on to the Big Bang story, and it was not invented to make the narrative grander. It was proposed in the early 1980s to solve specific problems that standard expansion leaves hanging in plain sight, problems that look like bookkeeping errors in the universe's earliest ledger. First is the horizon problem, which is really a problem of coordination across vast distances. The CMB temperature is nearly uniform across regions that, in an ordinary Big Bang picture, were never in causal contact. When we say causal, we mean something simple. No signal, not even light, could have travelled between those regions in time. In the ordinary Big Bang without inflation, distant patches of the CMB were too far apart for light to cross. The universe expands, and expansion sets a limit on who can talk to whom, because the fastest messenger is still limited by the speed of light. Use an analogy that fits the scale without shrinking the stakes, and keep the tension in the image. Imagine a stadium crowd asked to clap in perfect unison without hearing each other, while the stadium itself expands so quickly that sound cannot keep up. They can match only if they shared a cue earlier, before they were separated into silence. The CMB looks like the universe kept that cue, even across the sky, with tiny variations that are more like a controlled tremble than a chaotic roar. Inflation supplies the cue by changing the order of events, and that reversal is the key trick. Regions now far apart were once close enough to exchange heat and information, so they could settle toward the same temperature and the same basic conditions. Then, expansion accelerated so violently that the once connected patch was stretched beyond any later communication. Uniformity becomes a fossil of earlier contact, like a fingerprint preserved after the hand has long since vanished. Visually, this is where the documentary can slow down and let the geometry breathe. Picture a small, warm patch of space, almost featureless, floating in darkness, then watch it balloon outward, swallowing the frame until the original patch becomes unrecognizable. Second is the flatness problem, which is a problem of balance written into the Friedman equations. Today the universe appears extremely close to spatially flat geometry, meaning that on the larger scales we can measure, parallel lines behave as they do in Euclidean space. Curvature in cosmology is not about bending through a higher dimension in the everyday sense. It is about how distances and angles add up across enormous scales, and whether the universe is slightly open, slightly closed, or balanced on a razor's edge. In the Friedman equations, curvature behaves like a term that grows in relative importance over time during ordinary expansion. Without special initial conditions, even tiny curvature should have become obvious, because the universe has had billions of years to amplify the difference. The analogy is a pencil balanced on its tip for billions of years, and the absurdity is the point. If it starts even slightly tilted, it should fall quickly into visible curvature, and the longer it stays upright, the more suspicious the balance becomes. Near flatness therefore looks tuned, as if the early universe was set with impossible precision. Inflation changes the bookkeeping by diluting curvature as space expands exponentially, making the tilt fade into practical invisibility. Exponential expansion drives OK towards zero the way rapid zooming makes any surface look flatter. A sphere looks curved up close, but from far enough away it looks like a plane, and inflation creates that distance in the most extreme way. The universe can start curved and still end up looking flat within our horizon, which is the only region we can test. That caveat matters because inflation's power is not that it erases curvature everywhere, but that it can hide it beyond our observational reach. Third is the monopole problem, which is a problem of leftovers from high-energy physics. Many grand unified theories predict heavy magnetic monopoles formed in early phase transitions, when symmetries broke as the universe cooled from unimaginable temperatures. A monopole is the magnetic analogue of an isolated electric charge, a north without a south, and it is not forbidden by the deepest equations. In many models it is expected, and it is expected to be abundant, because phase transitions can produce defects the way freezing water can trap cracks. If monopoles were produced abundantly, they should still exist and dominate mass density, because they would be massive and stable. We do not see them, and their absence demands an explanation that does not rely on wishful invisibility. Inflation offers a simple escape that is brutal in its efficiency, and the brutality is almost poetic. It stretches space so much that any initial monopoles are diluted to near nothing, turning a potentially catastrophic relic into a statistical non-event. These motivations are not proofs, but they are pressure points that a successful early universe theory must address. Inflation is an attempt to relieve them with one mechanism rather than three separate fixes, and that unity is part of its appeal. Mechanism. Inflation posits a period when the energy budget was dominated by something vacuum-like, smooth, and persistent. In general relativity, that kind of energy drives accelerated expansion, because gravity responds not only to energy density but also to pressure. In everyday intuition, pressure pushes outward, yet in Einstein's equations, negative pressure can act like a repulsive gravitational effect. That is the counterintuitive hinge. A vacuum-like component with nearly constant density can make the scale factor speed up rather than slow down. The usual model uses a scalar field, often called the inflaton, as the simplest way to represent this behavior. A scalar field assigns a value to every point in space, like a temperature field, but it is a fundamental degree of freedom rather than a property of matter. What matters is its potential energy, a kind of stored energy landscape that shapes how the field evolves. If the field sits high on that landscape, its energy density can remain nearly constant, even while space itself expands dramatically. A nearly constant energy density behaves like a temporary cosmological constant, and the language is deliberately familiar. Pressure becomes negative, and the scale factor grows almost exponentially, meaning it multiplies by the same factor again and again in equal time steps. This is not the late-time dark energy story repeated verbatim, even if the mathematics rhymes. It is an early, brief episode at far higher energies, ending when the field changes state, and that ending is as important as the beginning. Inflation must end, or it would erase the hot Big Bang we know and leave a cold, empty universe. The field rolls down its potential, the vacuum-like phase ends, and energy is released into ordinary degrees of freedom. That release is reheating, the moment inflation hands the universe back to ordinary particles. The cosmos becomes hot and dense again, ready for nuclear synthesis and later recombination, with a thermal bath that resets the clock for familiar cosmic history. In visual terms, reheating is a dramatic shift in texture. The smooth, almost sterile expansion gives way to a glowing fog of particles, a seething plasma where photons scatter constantly, and matter cannot yet form stable atoms. Inflation therefore does two jobs at once, and the pairing is why it is so influential. It stretches space to solve horizon and flatness, Then it repopulates space with matter and radiation, restoring the conditions that lead to the CMB itself. The chapter's tension is that inflation also creates a new kind of boundary, and it is not a boundary we can fly to. It can make the observable universe a tiny remnant of a much larger whole, leaving us inside a bubble of visibility. Quantum fluctuations are the bridge from mechanism to evidence, and they are not optional decoration. In quantum field theory, fields cannot be perfectly smooth, even in their lowest energy state, because uncertainty is built into the vacuum itself. During inflation, microscopic fluctuations in the inflaton and in spacetime itself are stretched by the expansion. They are pulled from subatomic scales to astronomical wavelengths, crossing from the domain of quantum jitter into the domain of cosmic architecture. A useful way to picture this is to imagine ripples on a pond, except the pond is space, and the ripples are fluctuations in energy density. Inflation stretches the pond so quickly that tiny ripples become enormous swells, then freeze into place as they exit causal contact. When inflation ends, those stretched fluctuations become real density variations, slight overdensities and underdensities in an otherwise uniform sea. Gravity later amplifies them into the cosmic web of galaxies, clusters, and voids, turning faint initial differences into the large-scale structure we map today. This is the promised link between early physics and late structure, and it is one of inflation's most compelling successes. The CMB anisotropies at the 10⁵ level are the first visible imprint of that process, a delicate pattern of warm and cool spots spread across the sky. Inflation predicts the fluctuations should be nearly scale invariant, and that phrase has a precise meaning. It means the power in fluctuations changes only slowly with scale, so patterns look statistically similar whether you examine large patches or smaller ones. In many slow-roll models, the inflaton moves gradually down its potential, and that gradual motion produces a slight deviation from perfect scale invariance. The deviation is encoded in the spectral index NES, which measures how the fluctuation amplitude depends on wavelength. Observations find NS around 0.965, not exactly 1, and that small difference carries enormous weight. It suggests the primordial spectrum is slightly red, with a bit more power on larger scales, consistent with many inflationary potentials that are gently sloped. Inflation also predicts the fluctuations should be close to Gaussian, and this is a statistical statement with sharp teeth. Gaussianity means the fluctuations behave like a random field whose values follow a bell curve distribution, so the map is mostly described by its two-point correlations. Non-Gaussianity would imply extra structure in the statistics, hinting at more complicated dynamics or multiple fields. Planck and other datasets find the primordial fluctuations are indeed near Gaussian, which narrows the space of viable models without selecting a single winner. In the visuals, the CMB map is not just a pretty mosaic, it is a coded message, and the code is written in angular power spectra, correlation functions, and polarization patterns that require patient decoding. Inflation makes additional sharper predictions that are still being tested, and this is where the story becomes more suspenseful. One is the existence of primordial gravitational waves produced during inflation, ripples in spacetime generated by quantum fluctuations of the metric itself. These tensor fluctuations would also be stretched to cosmic scales, just as density fluctuations are stretched. They would leave a distinctive pattern in the CMB polarization called B-modes, a twisting, curl-like signature that cannot be produced by simple density perturbations alone. Polarization is subtle, so it helps to name what is being measured in plain terms. CMB photons scatter off electrons, and that scattering imprints a preferred direction in the light, creating patterns that can be decomposed into E-modes and B-modes. B-modes are not just another map feature, and they are not merely a technical curiosity. They would be direct evidence of inflation's energy scale, and of quantized gravitational degrees of freedom, tying the earliest universe to the quantum nature of spacetime. But the search is fragile because the sky is not clean, and the contamination is physically real. Dust in our galaxy can mimic B-mode patterns, and gravitational lensing by intervening matter converts E-modes into B-modes, adding a secondary signal that must be carefully removed. This is where earlier chapters promised messengers return with urgency, and the tone can tighten. Gravitational waves and polarization patterns could carry information from before recombination, beyond the last scattering screen, but only if we can separate primordial whispers from local noise. Experiments chase the signal with better detectors, colder instruments, and more precise calibration, often from the driest deserts and the highest plateaus. The goal is not a pretty image, but a robust constraint on the tensor to scalar ratio R, which compares gravitational wave power to density power. A detection would reshape the documentary's central question, because it would anchor inflation in a new kind of evidence. It would show that the earliest universe left a measurable imprint that survives every later epoch, from reheating to galaxy formation to the present dark energy era. A non-detection also matters, because it pushes inflation models toward lower energy scales and different potential shapes. It forces theorists to explain why the scalar fluctuations exist without a strong tensor counterpart, and it trims away models that predict too much gravitational wave power. Inflation also interacts with the topology question from Chapter 4, and the connection is geometrically elegant. If inflation lasted long enough, it would stretch any pre-existing curvature and any wraparound identifications beyond our horizon, turning a globally finite space into something locally indistinguishable from infinite. That means the absence of matched circles in the CMB becomes less surprising, and the disappointment becomes informative. Inflation can make a finite universe look infinite within the observable patch, not by changing topology, but by pushing its signatures outside our causal reach. Yet topology is not erased in principle, only hidden by scale, and that distinction keeps the mystery alive. Next-generation methods may still constrain it through subtle statistical anisotropies or large-scale correlation patterns, where even a faint deviation from perfect isotropy could be a clue. Inflation therefore deepens the theme that horizons are epistemic fences, not physical barricades. It can make the universe larger than any survey, even if the global space is finite, and it can make the whole feel like a category error. Now the story turns to the most unsettling implication, and the visuals can darken as the camera pulls back. Some inflation models suggest inflation is not a one-time event that ends everywhere, but a process that continues in some regions even as it stops in others. Eternal inflation arises when quantum fluctuations compete with the field's classical role, and the competition is probabilistic. In some regions the field falls and reheats, while elsewhere it fluctuates upward, delaying the end of inflation in those patches. Where it fluctuates upward, inflation continues and space expands faster than it decays, so the inflating volume grows without end. Even if many regions exit inflation, the regions still inflating can grow so quickly that they dominate the overall volume. The result is a multi-region cosmos, a landscape of outcomes produced by the same underlying rules. Reheated regions form bubble universes, also called pocket universes, embedded in a larger inflating background that keeps generating new pockets. Our observable universe would be one pocket, with its own reheating history and its own cosmic clock, and that phrasing matters. Our beginning would be a local event, the end of inflation here, rather than a single global start that applies to everything. Beyond our horizon could be more pockets, forever causally disconnected, not because they are far in the ordinary sense, but because expansion has severed any possibility of communication. The separation is dynamical, written into the history of the scale factor, not merely into distance. This is beyond the edge in the most literal sense, and it reframes the word edge itself. The edge is not a wall in space, but a horizon created by inflation's expansion and by later cosmic acceleration, a boundary defined by what can ever influence us. The narrative tension tightens because the beyond might not share our initial conditions, and that possibility carries a philosophical charge. Different pockets could inherit different field values, symmetry breakings, or vacuum states, depending on how inflation ended in each region. In some scenarios, that means different effective laws of physics, even if the deeper framework is the same. Constants could differ, particle spectra could change, and even the number of large dimensions could vary, making elsewhere not just distant but genuinely other. This is where inflation meets the cosmological constant problem from Chapter 5, and the connection is unsettlingly natural. If many vacua exist, our small dark energy value might be selected by environment rather than by a unique theory, because only certain values allow long-lived structure. That idea is controversial, because it shifts explanation towards statistics and selection effects, and away from inevitability. It also raises the hardest question in the series, which is what counts as a scientific claim when the objects of interest may be causally inaccessible. Inflation's defenders point to its successful predictions for perturbations, which are measurable and precise. Its critics point to model flexibility and to the difficulty of testing the global picture, because many inflationary potentials can be tuned to fit the same basic data. Eternal inflation is especially hard to test because other pockets are beyond any signal exchange, and that limitation is not technological. If they cannot affect us, their existence risks becoming metaphysics, a story that is internally consistent yet externally unreachable. Yet even an unreachable region can leave indirect traces if bubble collisions occurred in the early multi-region phase. Some searches look for circular anomalies in the CMB that could be collision scars, faint rings, or localized distortions that break the statistical uniformity. So far, no confirmed collision signature exists, and the silence has meaning. The absence constrains some models, but it does not eliminate the broader framework because the probability of observable collisions can be small even in an eternally inflating background. The chapter must hold both truths at once, without letting either become a slogan. Inflation is our best developed account of why the universe looks smooth, flat, and seeded with the right kind of randomness, and it connects those facts to known principles of field theory and gravity. Inflation also threatens to dissolve the meaning of a single beginning, and that is the emotional core of this chapter. If inflation is eternal to the future, and possibly to the past in some models, the beginning becomes local, a word that describes our region's history rather than the universe's totality. Our beginning would be the end of inflation in our region, not the start of everything, and that shift is profound. The vanishing past is not just earlier than the CMB, but earlier than our entire pocket's history, earlier than the very conditions that make our cosmic timeline coherent. This reframes the central question without answering it, and the uncertainty is part of the drama. If the universe has an edge in any meaningful sense, inflation suggests edges are horizons between regions, boundaries defined by causality rather than by matter. Beyond our horizon may be more space that looks like ours, or more space that never reheated, or other pockets with different histories. The boundary is causal, not material, and it is drawn by the finite speed at which information can travel. The hook from the opening returns with a sharper twist, and the camera can linger on the CMB as if it were a veil. At the top of the sky there is no wall, yet inflation implies there may be unreachable domains stacked beyond reach. Like layers of a reality we cannot peel back. We end with a transition that keeps momentum into the next chapter, and it should land like a door left ajar. If inflation suggests multiple regions, does that mean multiple universes? And what could outside our universe even mean? The edge may not be where space ends. It may be where our patch stops being the whole story. We began with a false edge in air, then found horizons made of light, limits drawn by photons and time, not by walls. When we look out, we look back, because distance is also delay, and the universe keeps its earliest chapters at the farthest reach. Inflation widened those horizons, and it hinted that our beginning could be local rather than absolute. In the standard picture, inflation is a brief era of accelerated expansion driven by a high-energy field, smoothing curvature and stretching tiny quantum ripples into cosmic structure. If that is true, then beyond the edge of space may not be a direction on a map. Beyond may be a larger reality in which our universe is one outcome, one reheated region, one history, one particular settling of fields. The word multiverse is not one idea, and it is not one claim. It is a family of hypotheses that share a theme. Reality could be bigger than our observable region, and elsewhere might mean more than simply far away. To keep rigor, we need a taxonomy that separates mild extensions from radical ones. 4 levels are often used, each enlarging the meaning of elsewhere, and each shifting what we mean by evidence. Level 1 is the simplest, and it stays inside the same space-time. Space could be much larger than our horizon, possibly infinite with more regions like ours, more galaxies, more stars, and more versions of the same cosmic history. In Level 1, the laws are the same everywhere, and the physics is familiar. The separation is only causal because light has not had time to reach us since the hot beginning. This is other worlds without new dimensions or new constants, and it requires no exotic engineering. It is a consequence of finite age and finite signal speed, the same logic that makes distant mountains hidden behind fog. Level 1 also reframes the edge as an information fence, not a boundary of existence. Beyond our particle horizon, there may be more galaxies and more history, continuing the same cosmic web beyond our sightline. Visually, it is a simple but unsettling image, a glowing sphere of visibility around us, embedded in a much larger darkness. The darkness is not empty, just unlit by information that has not yet arrived. Level Y has a quiet implication that can be easy to miss. If space is infinite, and matter is distributed roughly uniformly, then arrangements repeat, because there are only so many ways to arrange particles in a finite volume. That repetition is not magic, and it is not destiny, but it is combinatorics on a cosmic scale. Far enough away, there could be regions with the same large-scale patterns, and even regions that mirror our own history with tiny differences. Level 2 is different, and it is tied to inflation's most unsettling variant. In eternal inflation, inflation ends in some regions but continues elsewhere. So the process that made our smooth beginning never fully stops. When inflation ends locally, reheating fills that region with particles and radiation. The inflaton's stored energy converts into a hot plasma, and that region becomes a bubble universe, expanding from its own hot start. Other bubbles can form later, and they form in a background that keeps inflating. Between bubbles, space stretches so fast that bubbles separate faster than any signal can travel, making the separation dynamical rather than navigational. In many models, the inflating background behaves like a metastable state, a kind of false vacuum. Quantum fluctuations can trigger transitions to lower energy states, and each transition is a new bubble with its own effective low-energy physics. Level 2 allows different low-energy physics in different bubbles, depending on how fields settle into vacuum states. Constants could vary, symmetries could break differently, and the particle spectrum could change in ways that feel like alternate rulebooks. This is where the cosmological constant problem gains a new context. If many vacua exist, then many values of dark energy might exist across bubbles, and our small value becomes one draw from a vast menu. Historically, this idea gained traction as inflation matured from a clever fix into a framework with internal variety. Early inflation solved the horizon and flatness puzzles, but later work revealed that inflation, once allowed, can be hard to turn off everywhere. Level 3 comes from quantum mechanics, not cosmology, and it changes the meaning of branch. In the many worlds interpretation, the wave function never collapses, even when outcomes look definite to us. Instead, measurement-like interactions entangle systems with their environments. Outcomes decohere into effectively separate branches, each containing a consistent history, because interference between branches becomes vanishingly small in practice. Decoherence is not a mystical split, and it does not create energy from nothing. It is a redistribution of phase information into countless environmental degrees of freedom, air molecules, photons, vibrations, until recombining the histories becomes physically impossible. Level 3 does not place other worlds far away in space. It places them in the structure of quantum state space, where branches become mutually inaccessible, like radio stations that no longer share a common frequency. Level 3 also does not automatically add new laws, but it changes what we mean by a single outcome. The universe becomes a superposition of histories, and our experience is a path through that superposition. Level 4 is the most radical, and it is the hardest to anchor. It proposes that all mathematical structures exist physically, and our universe is one such structure, one consistent set of relations that can host observers. Level Phi treats the laws of physics as a selection from a space of consistent mathematics. It pushes why these equations into a deeper question about existence itself, where the boundary between physics and metaphysics grows thin. These levels are often discussed together, but they are not equally testable. Level 1 follows from standard cosmology if space extends beyond our horizon, and it is almost conservative in how little it changes. Level 2 depends on inflationary dynamics, and on a landscape of vacua. Level 3 depends on quantum interpretation, and Level 4 depends on a philosophical stance about mathematics and reality. The documentary's central question returns with new pressure. If the universe has an edge in any meaningful sense, is it a horizon between regions, or a boundary between realities that do not share a common space? We can sustain wonder without surrendering standards by asking a strict question. What would count as evidence, and what would count as a prediction that could have failed? In multiverse discussions, the strongest bridge to observation comes from Level 2. If bubble universes form, They might sometimes collide while inflation is ending, because bubbles nucleate within a shared inflating background. A collision would not send a spaceship-sized visitor, and it would not look like a doorway. It could leave a subtle imprint in our sky, because the early universe was a sensitive recording medium, like photographic film exposed while still developing. The best place to look is the CMB, our oldest electromagnetic messenger. The last scattering surface is a screen, and a collision could scar that screen with a pattern frozen into temperature and polarization. Visually, we return to that ancient light, a mottled sphere wrapped around us, coloured in faint reds and blues. Over it, we can imagine a translucent disk, slightly too smooth, slightly too sharp, hinting at an event outside our ordinary narrative. Predicted signatures vary by model, but common targets are localized anisotropies. Searchers look for circular or disc-like features, unusual cold or hot spots, and directional asymmetries that break the sky's expected statistical uniformity. Some models predict a temperature discontinuity across a boundary, while others predict a smooth modulation. Polarization patterns could also carry correlated anomalies, because polarization remembers the geometry of scattering in the primordial plasma. The challenge is that the CMB already has fluctuations from inflation's quantum seeds. A collision signal must be separated from the expected random field and from foregrounds, and those foregrounds are layered and stubborn. Foregrounds are not a minor nuisance, and our galaxy is not transparent. Dust emission glows in microwaves, synchrotron radiation traces spiraling electrons in magnetic fields, and instrumental systematics can paint patterns that masquerade as cosmology. Even if a feature is statistically unusual, it may not be unique to collisions. Cosmic variance limits certainty on the larger scales because we have only one sky, and the largest modes are sampled only a few times. A famous example is the CMB cold spot, which has inspired many explanations. It could be a rare fluctuation, it could be a line-of-sight void that cools photons through evolving gravity, or it could be something else entirely. So far, no bubble collision signature has reached broad consensus. The evidence remains tentative, and the absence also matters because it constrains some collision rates, ruling out the loudest versions of the idea. Yet the absence does not kill level 2, because many models predict collisions are unlikely to be visible. The multiverse can be real and still leave no accessible scar, because our bubble's history may be quiet and isolated. This is where the scientific boundary becomes sharp, almost audible. If a hypothesis can accommodate any outcome, then it risks becoming immune to data, and immunity is not the same as depth. Cosmologists respond by narrowing models until they make quantitative predictions. They compute expected distributions of collision signatures, then compare them to CMB maps, asking not only is there a spot, but how many spots should exist. They also look beyond temperature maps, because polarization and large-scale structure provide independent channels. Cross-checks matter because false positives are easy at the noise floor, where statistics can be seduced by chance alignments. The promised messengers from earlier chapters return as a constraint and as a hope. Primordial gravitational waves would test inflation's energy scale, shaping how eternal inflation could work and how the inflating background behaves. If B-mode polarization is detected with a clean primordial spectrum, it would strengthen inflation's core mechanism. It would not prove a multiverse, but it would raise its plausibility by supporting the engine that makes bubbles possible. If B-modes remain undetected and R stays very small, many high-energy inflation models weaken. Eternal inflation could still occur, but the space of viable scenarios shifts, and the most dramatic versions lose ground. The multiverse debate is therefore not detached from measurement. It is entangled with precision cosmology, with foreground subtraction, and with the limits of inference from one universe that we cannot step outside. Now the story tightens around a specific puzzle from Chapter 5. Dark energy looks like a cosmological constant with W near -1, and its value is tiny but non-zero, as though the vacuum has a faint but persistent pressure. Quantum field theory naively predicts vacuum energy far larger than observed. The mismatch is not a small error, and it is not a missing decimal point, but a crisis of scale that demands explanation. In quantum field theory, every field has a ground state with zero-point fluctuations. Summed across modes up to very high energies, the vacuum energy density becomes enormous, and yet gravity responds as if almost all of it is absent. One response is to search for a symmetry or mechanism that sets L to 0, then explain why it is not exactly 0. Another response is to treat L as environmental, varying across a larger ensemble where different vacua realize different values. Anthropic reasoning enters here, and it must be handled carefully, because it is often misunderstood. The argument is not that humans cause the constant, but that observers only arise in certain physical conditions. If L were much larger and positive, accelerated expansion would begin earlier and prevent galaxies from forming. Matter would thin out before it could collapse, and the night sky would never fill with long-lived stars. If L were large and negative, the universe could recollapse quickly. Structure might begin, but the cosmic clock would run out, compressing the window for chemistry, planets, and biological evolution. In a multiverse with many values of L, most regions would be sterile. We should expect to find ourselves in a rare region where structure can persist long enough, because only such regions can host the act of noticing. This can make the observed small value less surprising, because selection effects bias what can be observed. It turns the question from why this value to why we can measure any value at all, given the preconditions for measurement. But anthropic reasoning is also criticized, and the criticism is not only emotional. It can be hard to define the ensemble of universes, the measure over that ensemble, and the probability of observers within it. The measure problem is technical and severe in eternal inflation, because the process can produce infinite volume and infinite bubbles. Naive counting gives infinities that depend on how you regulate them, and different regulators can disagree. Different measures give different predictions, which threatens objectivity. If probabilities depend on arbitrary cutoffs, then the framework risks losing predictive power, because the numbers become artifacts of bookkeeping rather than features of nature. There is also a deeper worry about explanation that reaches beyond mathematics. Some physicists argue that anthropic arguments can become a substitute for dynamics, replacing mechanism with selection when a mechanism is difficult to find. Others argue that selection is a legitimate part of science when the ensemble is real and the distribution is computable. They point to how observational bias is handled in other fields, where the fact of being an observer is itself a filter. The documentary must hold this tension without resolving it too quickly, because the tension is the point. The multiverse can feel like an escape hatch, yet it can also feel like a clue about how laws emerge from deeper structure. So what counts as a prediction in this territory, where direct travel is impossible and replication is denied? A prediction is not a story that fits after the fact, but a constraint on what we should see and what we should not. For level 1, predictions are subtle because it mostly extends what we already assume. It predicts statistical homogeneity beyond our horizon, but we cannot sample it directly, so support comes from consistency within what we can measure. Still, level 1 can be indirectly supported if the universe is close to flat and inflation lasted long enough. In that case, a much larger space is the natural continuation of the same geometry, and the edge becomes merely our limit. For level 2, predictions must connect to inflationary observables in our bubble. They include the spectrum of primordial perturbations, possible non-Gaussianity, and constraints on reheating that shape how our hot beginning was set. They also include the absence or presence of collision signatures, but only once models specify rates and amplitudes. Vague collisions are not predictions, and quantified collisions are, because they can be ruled out. For level 3, the challenge is different because it shares all standard quantum predictions. Many worlds is hard to test because it reproduces the same measurement statistics, leaving the debate to hinge on explanation and ontology. Debates then shift to whether explanatory economy counts as evidence, or whether only new empirical consequences count. The boundary between physics and interpretation becomes visible, and it can feel uncomfortably sharp. For level 4, the scientific tether is weakest, because almost any consistent mathematics could be said to exist. Without a way to weight structures, it risks explaining everything and nothing, dissolving prediction into an ocean of possibilities. Falsifiability is often invoked here, but it is not a simple gate. Some theories are hard to falsify, yet still scientific if they generate constrained, risky predictions elsewhere, and if they cohere with a broader web of tested ideas. Inflation itself faced this debate, and it earned credibility by predicting a nearly scale-invariant, nearly Gaussian spectrum. The multiverse must seek an analogous anchor, something that can be computed before the data, not narrated after. Cosmologists try to keep the idea tethered by focusing on what is measurable inside our horizon. They test inflationary parameters, search for anomalies, and refine models that imply specific signatures, even when those signatures are faint. They also ask whether multiverse frameworks can predict correlations among constants, not just their existence. If a landscape predicts linked variations, those links could be indirectly tested by how tightly our constants fit the allowed patterns. Yet the core tension remains, and it is the chapter's emotional engine. The more we enlarge reality, the harder it becomes to prove, and the more our universe looks like a single room lit briefly in a vast, dark mansion. Our universe begins to look like one lit chamber in that mansion, with windows that are not glass. The walls are not stone, they are horizons, and the corridors may be real even if we never walk them. Visually, the mansion is not built of bricks but of geometry, expanding rooms, branching hallways, and doors that are really phase transitions in fields. Somewhere, far beyond any telescope, other rooms ignite with their own first light. This is not a retreat into mysticism, and it is not a claim that anything goes. It is a recognition that cosmology operates at the boundary where inference meets limitation, and where the universe offers clues without guarantees. We should be honest about what we know, because honesty is part of the drama. We have strong evidence for expansion, for the CMB, for dark matter, and for accelerated expansion, each supported by multiple independent measurements. We have suggestive evidence for inflation through the perturbation spectrum, but we still seek decisive signatures like primordial B modes. We have no confirmed evidence for other bubbles, and we do not pretend otherwise. And yet the question persists because the universe keeps hinting at hidden scale. Near flatness, horizon structure, and the smallness of L all point toward a deeper accounting, as though our equations are shadows cast by a larger framework. Transition. If beyond is not a place, then the next step is not farther outward. The next step is downward into the rules that make space possible. If other universes exist, they may not be next door in space, and they may not be reachable even in principle. So we pivot to the fabric beneath space itself, where space-time might be emergent and where elsewhere could mean underneath. The central question remains, sharpened rather than answered. If the universe has an edge in any meaningful sense, it may be the limit of our causal patch. Beyond it may be more cosmos, other outcomes, or deeper laws that do not live inside space at all. If beyond is not a place, then the next step is not farther outward. The next step is downward into the rules that make space possible. We have chased edges made of air, light, and expansion, and each edge slid away as our instruments improved. On screen, the camera pulls back from galaxies into the faint CMB glow, then keeps pulling until the image becomes pure noise. Now the edge becomes a failure of description, a seam where our best theories stop agreeing. The universe is still there, but our language for it starts to tear. General relativity treats space-time as smooth geometry, shaped by mass and energy, with curvature telling matter how to move. Quantum mechanics treats reality as fields and probabilities, restless even in vacuum, where fluctuations briefly borrow energy and give it back. Each theory is spectacular inside its domain, and each becomes suspect at extremes where its assumptions break. The universe forces those extremes in two places, at the beginning and inside black holes. Historically, this split was not obvious at first, because each theory solved a different crisis. Einstein's gravity explained Mercury's orbit and predicted light bending, while quantum theory explained atoms, spectra, and the stability of matter. Singularities are not objects we can point to with a telescope, like a planet or a star. They are places where equations demand infinite density and curvature, and that demand is a warning, not a destination. A singularity is the map ending, not the territory ending, and the distinction matters. It says the model has been pushed beyond its valid range and new rules must take over. In practice, singularities appear when we extend classical equations past where they were ever tested. The mathematics keeps going, but the physical interpretation becomes unmoored, like coordinates drawn over a region the cartographer never surveyed. The Big Bang singularity is the sharpest example, because it sits behind every horizon we discussed. If time begins at a point of infinite curvature, physics becomes a sentence without grammar, with no earlier clause to anchor cause and effect. Black hole singularities repeat the problem in miniature, hidden behind event horizons that act like one-way doors. They are laboratories we cannot enter, yet their existence pressures theory from the outside, because the horizon's behavior is observable. The conflict is not philosophical, It is mathematical and operational, and it shows up in calculations. Quantum fields on curved spacetime work until the curvature becomes too strong, then back reaction demands a quantum spacetime, not a classical stage. Back reaction is the key complication, because energy in quantum fields gravitates too. When fluctuations become large, they do not merely ride on geometry, they reshape it, and the separation between matter and spacetime stops being clean. To name that regime, we use the Planck scale, where gravity becomes as strong as other forces. It is around 10^35 meters and around 1019 giga-electron-volts, far beyond any accelerator we can build. Those numbers are not arbitrary, because they come from combining C, G, and H into a unique set of units. They mark the scale where spacetime fluctuations should be unavoidable, like foam beneath a calm surface, except the foam is geometry itself. Visually, imagine a ruler shrinking until its tick marks blur, while the grid behind it begins to jitter and buckle. The closer we zoom, the more distance looks like a statistical concept rather than a fixed backdrop. At the Planck length, the idea of a point may fail, because localization requires energy concentrated into a region. Put enough energy into a tiny volume, and it collapses into a black hole, hiding the very region you tried to resolve. So the usual picture of measuring smaller and smaller distances breaks in a self-defeating loop. The act of probing creates gravity strong enough to erase the probe's target, turning precision into a kind of censorship. This is not just a poetic limit, it is a quantitative one, tied to the uncertainty principle and gravitational radius. When the Schwarzschild radius of the probe energy matches the region size, inside becomes inaccessible by definition. Time may fail too, because clocks are physical systems with quantum uncertainty and finite resolution. In a violently fluctuating geometry, there may be no single global time to count, only local notions that disagree. General relativity already teaches that time depends on motion and gravity, but it still assumes a smooth metric. Quantum gravity threatens the metric itself, so the very parameter we use for evolution becomes part of the uncertainty. This is where the documentary's central question sharpens in an unexpected way, and the camera lingers on a horizon line dissolving. If the universe has an edge, it may be the boundary of classical spacetime itself. Quantum gravity is the name for the missing theory that unifies these limits, and it is more like a research continent than a single city. It is not one proposal, but a frontier where multiple frameworks compete, cross-pollinate, and sometimes converge. One path begins by changing what the fundamental objects are, because points are mathematically convenient but physically dangerous. If particles are points, interactions at zero distance become too violent, and infinities proliferate in calculations. Those infinities are not mere bookkeeping errors, because they signal sensitivity to arbitrarily small scales. Renormalization tames many quantum field theories, but gravity resists the usual cure, suggesting that the underlying assumptions must change. String theory replaces points with one-dimensional strings, whose vibrations look like particles in our detectors. Smearing interactions over a finite length can soften the worst divergences, because collisions are no longer perfectly localized. In string theory, gravity is not added by hand, it appears as a vibration mode of a closed string. The graviton emerges naturally, which is why the framework is taken seriously, even by skeptics who dislike its vastness. The idea has a history that reads like a scientific pivot, because strings were first explored for the strong force. When quantum chromodynamics took that role, strings survived by revealing gravity in their spectrum, turning an apparent failure into a new direction. But strings are consistent only in more dimensions than we see, and that requirement is rigid. The extra dimensions are not optional decoration, they are required by the mathematics, because anomalies cancel only in specific dimensional counts. To reconcile that with experience, the extra dimensions are compactified, curled up at tiny scales beyond present resolution. They can be shaped in many ways, and each shape changes low-energy physics, like a musical instrument changing the notes it can produce. Compactification turns geometry into a kind of code for particles and forces, because topology and symmetry control what fields can exist. Different shapes can yield different spectra, symmetries, and coupling strengths, which is why the details matter. On screen, the extra dimensions can be rendered as intricate folded spaces, like microscopic origami threaded through every point. The visual should feel intimate and alien, hidden structure packed into what looks like emptiness. This connects back to Chapter 7's landscape idea, but with a concrete mechanism that generates variety. Many possible compactifications imply many possible effective universes, even within one deeper theory, and the selection problem becomes unavoidable. The edge question then becomes layered, because beyond can mean more than one kind of beyond. Beyond our horizon could be more of the same space, but beneath our space could be extra directions we cannot access. String theory also suggests brains, extended objects of various dimensions that strings can attach to. A brain can host open strings, which behave like the particles and forces we know, while closed strings roam more freely. In brain-world scenarios, our visible universe could be a three-dimensional brain embedded in a higher-dimensional bulk. The higher-dimensional bulk could contain gravity and perhaps other hidden fields, making our cosmos a surface rather than the whole. That picture changes what outside means without adding a new location in our familiar space. Outside could mean off the brain, into the bulk, along dimensions we do not traverse, like stepping out of a sheet into the room. It also changes what an edge could be, because confinement can mimic boundaries without physical walls. Matter might be trapped to the brain, while gravity leaks, weakening with distance in the bulk, and that leakage would subtly reshape inverse square expectations. Such leakage is constrained by experiments, from tabletop tests of gravity at sub-millimeter scales to collider bounds on missing energy. So far, no deviation has forced extra dimensions, but the parameter space is large, and null results still carve it down. The brain idea also offers a new way to imagine the Big Bang, and the visuals can shift from a point explosion to converging membranes. Instead of a singular beginning of everything, it could be an event within a larger arena, with a before and an after. Ekpyrotic and cyclic models use that possibility, treating the hot Big Bang as a brain collision. In this view, our expansion begins when brains approach, collide, and reheat, converting motion in the bulk into the thermal bath we infer. The ekpyrotic phase is not inflation, and the difference matters for both dynamics and signatures. It uses slow contraction with a very stiff equation of state to smooth and flatten the universe before the bang, suppressing dangerous anisotropies. Inflation stretches space to erase curvature and homogenize conditions, amplifying quantum fluctuations into cosmic structure. Ekpyrosis compresses and dynamically suppresses anisotropies, then converts contraction into expansion through a bounce-like transition, often requiring careful control of instabilities. These models aim to address the same puzzles inflation solved, but with different dynamics and different vulnerabilities. They often predict negligible primordial gravitational waves, unlike many inflationary scenarios, because the mechanism does not generically excite large tensor modes. That prediction ties back to the promised messengers from Chapter 3, and the camera returns to polarization maps. If future CMB B-mode searches find a clean primordial tensor signal, many ekpyrotic models strain, because they would need extra mechanisms to imitate it. If B-modes remain absent at very low R, ekpyrotic and low tensor inflation models both remain viable. The edge of knowledge becomes a narrowing corridor, not a single door, and the corridor's walls are built from data. Cyclic versions go further, proposing repeated epochs of expansion and contraction, with the bang as a recurring transition. Each cycle can dilute entropy in specific constructions, though the thermodynamic bookkeeping is contested, and the question of accumulated disorder never fully disappears. The observational challenge is that cycles can hide their tracks, because later phases can overwrite earlier imprints. A successful cyclic model must leave distinctive signatures in perturbation statistics, non-Gaussianity, or relic backgrounds, and those signatures must survive the smoothing dynamics. Another path to quantum gravity begins by quantizing geometry itself, rather than replacing particles with strings. Loop quantum gravity starts with general relativity, then rewrites it in variables suited to quantization, treating connections and areas as primary. In this approach, spacetime is not fundamentally continuous, even if it looks continuous at human scales. Areas and volumes come in discrete quanta, like a granular fabric whose smoothness is an approximation, the way a photograph becomes pixels when magnified. The discreteness is not imposed as a stylistic choice, but arises from the quantization procedure and the theory's operators. The spectrum of area and volume has a smallest non-zero value, which implies a built-in cutoff against infinite compression. Discrete geometry changes what happens at extreme curvature, because the classical divergence is no longer allowed. Instead of diverging to infinity, curvature can reach a maximum, and the singularity can be replaced by a transition governed by quantum geometry. In loop-inspired cosmology, the Big Bang becomes a big bounce, a phrase that changes the emotional tone of the origin story. A prior contracting branch transitions through a quantum regime into our expanding universe, with density peaking near the Planck value. The bounce is not a free miracle. It comes from modified dynamics at Planck density, where quantum corrections dominate. Quantum geometry produces an effective repulsion that prevents infinite compression, like pressure arising from the discreteness of the underlying structure. Visually, the timeline can be drawn as a narrowing funnel that never pinches to a point, then opens again. The moment of maximum density glows, not as an endpoint, but as a bridge between two classical-looking eras. This offers a different answer to the map-ending problem, and it preserves the idea that physics continues. The map continues, but the coordinates we used must be replaced by a deeper description, because smooth space-time was only a large-scale approximation. Loop quantum gravity and string theory do not simply disagree on details, like competing parameter choices. They disagree on what is fundamental, on whether space-time is built from strings in higher dimensions, or from quantized geometry in 4, and that is a profound fork. Both face the same demand to connect to measurable predictions that can be checked rather than admired. Quantum gravity cannot live only at unreachable energies. It must leave traces in accessible phenomena, even if those traces are subtle. Those traces could appear in the early universe, because the beginning was the highest energy laboratory we have access to. Primordial gravitational waves, spectral distortions, and non-Gaussianity become forensic tools, letting us infer processes we cannot recreate. They could also appear near black holes, where horizons and quantum fields interact in extreme conditions. Hawking radiation already hints that gravity and quantum theory must share a consistent language, because it is derived by mixing quantum fields with curved space-time. Hawking's result makes a new kind of edge, an information edge, and the visuals can shift to particles escaping a dark sphere. If black holes evaporate, what happens to the information about what fell in, and where does it go? The information problem is not a side plot, it is a stress test of space-time itself, because it pits principles against each other. It asks whether quantum mechanics remains unitary, or whether horizons destroy information, turning pure states into mixed states. Modern ideas suggest information is not lost, but encoded in subtle correlations that are hard to extract. Holography proposes that a region's physics can be described by degrees of freedom on its boundary, a radical compression of description. Holography turns the edge metaphor into mathematics, and it gives the boundary a new authority. The bulk can be emergent, built from entanglement patterns in a lower dimensional description, so geometry becomes a consequence rather than a starting axiom. If that is true, then outside becomes ambiguous in a deeper way than extra dimensions suggest. The fundamental description might not live in space at all, and space could be a derived, approximate concept, like temperature emerging from molecules. This is the deeper tension of the chapter, and it reframes every earlier horizon we used as a guide. We thought the edge was where light stops, but perhaps the edge is where space-time stops being fundamental, and our intuitions lose their footing. Extra dimensions and brains make outside a higher dimensional arena that still feels spatial, even if hidden. Emergent space-time makes outside a different category, more like underlying relations than a place, and that shift is harder to picture. Both possibilities keep the central question alive, but they change its grammar, and grammar matters in science. What lies beyond the edge of space might be the rules that generate space, not more space, and the difference is everything. We can connect this to dark energy, because acceleration feels like a property of space-time itself, not a simple substance. If vacuum energy is miscounted by quantum field theory, then our notion of vacuum may be incomplete, and the mismatch becomes a clue. The cosmological constant problem becomes a clue about quantum gravity, because it is a clash of scales. It suggests we do not yet know how space-time responds to quantum vacuum, or how vacuum is defined in a dynamical geometry, where empty depends on the observer. Some approaches treat dark energy as a field, not a constant, with W possibly evolving over cosmic time. If W differs from -1, it could hint at new degrees of freedom, or at modified gravity, and the sky becomes a laboratory again. If W is less than -1, the future could end in a big rip, tearing bound structures apart as expansion accelerates without limit. That extreme fate would imply exotic physics, and it would demand consistency with quantum stability, because negative energy behaviors can be dangerous. If W stays near -1, the future approaches de Sitter-like isolation, a quiet but relentless horizon. Galaxies beyond the event horizon fade, and the observable patch becomes a lonely island, with the night sky slowly emptying as signals can no longer reach us. Either way, horizons become more than geometry. They become a limit on what can ever be known. The universe can be real beyond our reach, yet forever causally silent, and that silence is a physical statement. This returns us to the earlier promise about messengers that can cross deeper time, and the visuals can layer transparent shells of decoupling. Neutrinos decouple earlier than photons, and primordial gravitational waves could come earlier still, carrying information from epochs we cannot see. Detecting the cosmic neutrino background is brutally hard, because the relic neutrinos are cold and interact weakly. Yet a detection would open a window before recombination, letting us test parts of the thermal history now inferred indirectly. Detecting primordial gravitational waves would probe energy scales near the earliest moments, because tensor modes remember the expansion rate. Even upper limits already shape theory, because they rule out broad classes of high tensor inflation models. Yet even these messengers may not reach the Planck era cleanly, and that is part of the mystery. Quantum gravity could scramble the signal, or replace the notion of a single beginning with a transition, so the earliest time might not be a time we can parameterize. So the edge keeps retreating, but it also keeps changing shape as our questions mature. It is no longer a boundary in space, but a boundary between effective theories, between approximations that work and principles that must be reconciled. We can say what the edge is not, with increasing confidence and with fewer metaphors. It is not a wall you can approach, and it is not a rim where the universe ends, because every physical horizon we meet is a horizon of access. The edge is where our descriptions stop being mutually consistent, where two successful languages contradict each other. It is where smooth space-time and quantum fields demand a deeper reconciliation, and where singularities act like warning lights on the dashboard. String theory offers hidden dimensions and brains, making our universe a surface in a larger bulk, with geometry encoding particle properties. Loop quantum gravity offers discrete geometry, making the Big Bang a bounce instead of a singularity, with curvature capped by quantum structure. Ekpyrotic and cyclic models offer collisions and repeated epochs, turning the bang into an event rather than an absolute start. Each option shifts what beyond could mean, and each faces hard tests that turn philosophy into measurement. The stakes are not only about origins, they are about what reality is made of, at the most basic level. If space-time is fundamental, quantum gravity must quantize it consistently, without contradictions or infinities that signal missing ingredients. If space-time is emergent, quantum gravity may be a misnomer, and gravity may be a collective behavior of deeper degrees of freedom. The fabric under space could be information, entanglement, or something we have not named, and the universe becomes less like a stage and more like a computation. Transition. If space-time can emerge, then perhaps the truest edge is informational, defined by what can be known. The next chapter follows that idea to its sharpest form, where physics meets limits that feel almost philosophical, but remain quantitative. We ask whether the universe is bounded not by matter, but by computation, entropy, and the limits of measurement itself. If space-time can emerge, then perhaps the truest edge is informational, defined by what can be known. We started with a sky that seemed to end, then learned the ending was a gradient of brightness and distance. We chased that feeling outward, and every time the boundary moved, because the universe kept offering deeper layers of structure. The horizon was never a painted line on the dome above us. It was a rule about signals and about which events can ever matter to us. Now the story reaches its sharpest turn, because the edge stops being scenic and becomes mathematical. Horizons do not only limit travel through space, horizons limit knowledge, and they do it with equations that refuse to negotiate. A horizon is a one-way filter on information, defined by the causal structure of space-time. It divides what can influence us from what cannot, even if both regions exist in the same overall geometry. In relativity, causality is drawn by light cones, tilted, stretched, and warped by gravity. A horizon is where those cones tip so far that outward stops being a future option. Cosmic horizons do this on the larger scale quietly and impersonally. Black holes do it in miniature, and they do it with brutal clarity, an edge so sharp that even light cannot file an appeal. On screen, the contrast is immediate. A bright accretion disk, a dark centre, and a ring of lensed starlight that seems to wrap around emptiness. A black hole is not defined by a surface you can touch, or even by a material boundary. It is defined by an event horizon, the boundary of no return, which is global rather than local. You cannot detect the horizon with a meter stick at a single moment. You define it by asking a question about the entire future. Which events can still send light to infinity? Outside the horizon, light can still escape to distant observers, though it may be redshifted and delayed. Inside, every future-directed path points inward, and escape becomes impossible in the same way tomorrow is unavoidable. The geometry does not merely block motion, it rearranges the meaning of forward, so that falling inward is as natural as time passing. That sounds like a simple geometric statement, until quantum fields enter the scene and refuse to stay quiet. Then the horizon becomes a thermodynamic object, with temperature, entropy, and a kind of statistical bookkeeping. The edge begins to behave like a physical system, even though it is made of space-time itself. Hawking's insight begins with a premise that sounds almost philosophical, but it is experimentally grounded. Even empty space is not empty, because quantum fields fluctuate around their lowest energy state. In quantum field theory, every point is threaded by fields, and the vacuum is a restless baseline rather than a true void. Those fluctuations are not optional decorations. They are enforced by uncertainty relations that limit how sharply a field and its conjugate momentum can be pinned down. If you zoom in on a region of space, the vacuum looks like a sea of ephemeral excitations. Most of them annihilate before they can be named, yet their statistical effects are real. Near a horizon, those fluctuations are split by the causal boundary, and the split matters. What one observer calls vacuum, another can call a bath of particles, because particle content depends on how you slice time. The horizon changes which modes are accessible, and accessibility is part of what a particle even means. The result is Hawking radiation, a slow leak of energy from the black hole. It is not a classical jet, and it is not matter squirting through a crack. It is a quantum effect tied to curved space-time, where the vacuum state for an infalling observer differs from the vacuum state for a distant one. In the simplest picture, pairs of excitations appear near the horizon. One falls in, one escapes, and the whole loses mass, as if it were paying an energy debt. The image is useful for intuition, but it is not the real mechanism. The deeper story is about field modes stretched by gravity, and about how horizons force a division of the quantum state. The deeper point is not the cartoon of pairs, but the accounting rule it hints at. Horizons force observers to trace out inaccessible degrees of freedom, because no measurement can reach behind the causal barrier. When you ignore what lies behind the horizon, the remaining state looks thermal. Temperature appears because information has been hidden in correlations you cannot access. This is the same logic that makes a subsystem look warm even when the whole is pure. Entanglement can mimic heat, because the reduced density matrix carries ignorance that is not mere laziness. It is enforced by the geometry, and geometry is enforced by gravity. So a black hole has a temperature set by its surface gravity, which measures how strongly spacetime accelerates near the horizon. The formula is simple in shape. Higher surface gravity means higher temperature. Smaller holes are hotter, and they evaporate faster, because their curvature is more intense at the edge. For a stellar mass black hole, that temperature is far colder than the cosmic microwave background, so the radiation is essentially drowned. For a hypothetical tiny black hole, the temperature would be enormous, and the evaporation would be violent. The same equation spans both extremes, which is part of its eerie elegance. That temperature implies entropy, because thermodynamics demands it. If a black hole can heat things, it must count microstates, even if we do not yet know their detailed identity. Entropy is not just messiness, it is the logarithm of how many microscopic configurations correspond to the same macroscopic appearance. Bekenstein's argument makes the horizon the key, and it arrived before Hawking's calculation cemented it. He asked what happens when you drop a box of entropy toward a black hole. If the entropy disappeared, the second law would fail, because the outside world would lose track of states. The resolution was radical and precise. The entropy must be attributed to the black hole itself, and it must scale with the horizon area, not the volume inside. The horizon behaves like a ledger, an accounting surface that grows when information falls in. This is the first shock to ordinary intuition, because everyday entropy scales with volume. More room means more molecules, more arrangements, more microstates. We learn to think of information as something that fills space, like gas in a container. For black holes, the bookkeeping flips, and it flips with mathematical force. The maximum entropy in a region is proportional to the area of its boundary, not the volume it encloses. The limit is not about how much matter you can pack inside. It is about how much information the boundary can encode without collapsing into a black hole. The formula is precise and unforgiving, and it carries the constants of nature like a signature. 1/4 of the horizon area, measured in Planck units, gives the entropy. The Planck area is tiny beyond intuition, built from Newton's constant, Planck's constant, and the speed of light. Yet the formula insists that reality counts in those units. Area law entropy is not a metaphor. It is a quantitative statement that links gravity, quantum theory, and information in a single line. When physicists saw it, they recognized a clue with the weight of a law. Something about space-time was acting like a quantum information system. It also turns the horizon into a laboratory, even if we cannot touch it. We cannot enter it and return, but we can calculate what it must do to remain consistent. In physics, consistency is not aesthetic. It is the demand that different principles do not contradict when pushed to extremes. That consistency is tested by a paradox that refuses to die, because it lives at the intersection of two successes. If black holes evaporate, what happens to the information that fell in? The question is sharp because we know how quantum systems behave, and we know how horizons behave, and the two stories collide. In quantum mechanics, time evolution is unitary, which means information is preserved in principle. Pure states evolve into pure states, even if they become complicated and practically unrecoverable. The equations do not permit true erasure, because erasure would break reversibility at the fundamental level. Thermal radiation, by contrast, looks like a mixed state, a statistical blur. If evaporation ends in featureless heat, the outgoing radiation seems forgetful, as though it carries only temperature and not history. The black hole would behave like a shredder that turns a library into ash. So the naive story predicts information loss, and it predicts it cleanly. A pure state collapses into a mixed state, and quantum theory's core rule breaks. That is not a small crack in the wall. It is a failure of the structure that makes probabilities consistent across time. This is the black hole information paradox, and it is not a philosophical puzzle dressed in cosmic clothing. It is a clash between two frameworks that have earned our trust with experiments. General relativity says the horizon hides the interior, and quantum mechanics says the full state must remain recoverable in principle. If information is truly lost, then quantum predictions become inconsistent in a way that spreads. Probabilities would fail to add up across time, and physics would lose control of cause and effect at the quantum level. The worry is not merely about black holes. It is about whether quantum theory can be the foundation we think it is. If information is not lost, then the horizon cannot be a simple one-way curtain. Something about space-time must change at the edge, or else the radiation must carry subtle structure. The paradox forces a choice: modify quantum mechanics, modify gravity, or discover a hidden layer where both remain intact. Early proposals tried to accept loss, then pay the price. They faced problems with energy conservation and with the structure of quantum theory, including how to define a consistent evolution. Other proposals tried to keep unitarity by modifying the horizon, implying correlations in Hawking radiation that encode what fell in. That encoding must be extraordinarily delicate, because the radiation looks thermal locally. A detector near the black hole would measure a spectrum like a warm object, with no obvious messages embedded. Yet globally it must carry hidden pattern, spread across many quanta, like a code that only appears when you compare the whole sequence. This shifts the question from particles to entanglement, the quiet architecture of quantum correlations. The outgoing radiation is entangled with what remains, until late times force a reckoning. If the black hole disappears completely, the entanglement cannot simply hang in the air. It must be transferred, rearranged, or resolved. As evaporation proceeds, entanglement entropy should rise, then fall if information escapes. That expected curve became a target for theory, because it offers a quantitative diagnostic. The turning point, often called the page time, marks when the radiation begins to carry more of the system's information than the remaining black hole does. Modern calculations using quantum extremal surfaces reproduce that curve in controlled settings. They suggest the radiation can purify, consistent with unitarity, even while the near-horizon experience remains smooth. The method is technical, but the message is simple. The accounting can work if we accept a surprising geometry of information. But the cost is conceptual, and the cost is the point of the chapter. The calculation treats parts of space-time as if they belong to the radiation's description through an island region. The boundary of what counts as the system shifts, as though space-time itself participates in the bookkeeping. The island idea sounds like a trick, yet it matches deeper hints from holography and entropy bounds. It says the boundary of a system can include pieces that look interior, depending on which correlations are accessible. In other words, where information lives is not always the same as where matter is. That is a clue about emergent geometry, and it is a clue with teeth. It suggests space-time regions are not fundamental containers, but elements in an information accounting. The map of space may be a derived summary of entanglement patterns, rather than the stage on which entanglement happens. The paradox also sharpened another tension that is easy to miss. If information escapes, where was it stored while the whole existed? If it was in the interior, the horizon blocks it. If it was on the horizon must have microscopic degrees of freedom that we do not see in classical gravity. One answer is that it's stored on the horizon itself, though not as a literal film. Think of it as quantum degrees of freedom associated with the boundary, capable of encoding states in a way that scales with area. The horizon becomes less like a line and more like an interface, where gravity and quantum theory negotiate. This is where the holographic principle enters, not as poetry, but as a proposed law. The physics in a volume may be encoded on its boundary, with the bulk description acting like an efficient reconstruction. The principle was motivated by black holes, but it reaches beyond them, because it speaks about information limits in any region. Holography generalizes the black hole area law. It says the maximum information content of a region scales like area, not volume, and that the bound is saturated by black holes. If true, then our usual picture of space is overcounting. The bulk may be a redundant description of boundary data, like a 3D image stored on a 2D plate. That idea has an existence proof in certain spacetimes, where it is not merely plausible, but precise. In anti-de Sitter space, gravity in the bulk is dual to a quantum field theory on the boundary. The boundary is lower dimensional, yet it contains the full content of the higher dimensional gravitational world. This is ADS-E-CFD correspondence, and it emerged from string theory in the late 1990s as a shock of coherence. It equates a higher dimensional gravitational theory with a lower dimensional non-gravitational theory. The duality is not approximate in its best understood forms. It is a mathematical identity, linking observables across the two descriptions. In that framework, a black hole in the bulk corresponds to a thermal state in the boundary theory, and the match is not superficial. Entropy and temperature align across the duality, and so do dynamical processes like relaxation and transport. The boundary theory, with no gravity at all, still knows about horizons through thermodynamics. Even more striking, aspects of bulk geometry can be reconstructed from boundary entanglement. Relations like the Ryu-Takayanagi formula tie the area of certain bulk surfaces to entanglement entropy in the boundary state. Spacetime becomes readable as an information pattern, as if geometry were a shadow cast by quantum correlations. This is the climax of the chapter's logic, and it changes the meaning of edge. The edge is no longer only where light cannot pass. The edge is where description compresses, where a higher dimensional story can be rewritten in fewer dimensions without losing content. But we must be careful with the leap to our universe, because the details matter. Add space has negative curvature and a time-like boundary, unlike our observed cosmos. Our universe appears closer to de Sitter space on large scales, with positive vacuum energy and an accelerating expansion. De Sitter space has a cosmological horizon, not a spatial boundary at infinity. Observers are surrounded by a horizon that depends on their world line, like a private edge that travels with them. Two observers can disagree about which events are forever out of reach, because their causal patches differ. That horizon also has temperature, by the same logic that gave Hawking radiation. An observer in de Sitter sees a thermal bath, even if the universe contains no ordinary matter. The temperature is set by the expansion rate, and it is a property of the horizon, not of any particular object. The de Sitter temperature is tiny for our current expansion rate, far below any practical measurement. Yet its existence matters because it ties cosmic acceleration to thermodynamics. It tells us that expansion is not just kinematics. It has an informational cost and a statistical character. A horizon with temperature implies entropy, and de Sitter space has an entropy proportional to the area of its cosmological horizon. The number is staggering, yet finite, which is the unsettling part. It suggests that the universe, if it approaches de Sitter, may have a maximum entropy accessible to any observer. That is a limit on information, and it is not merely about engineering. It is a bound written into the geometry, as if the universe were telling each observer, here is the maximum number of distinct states you can ever, even in principle, distinguish. The limit is not about how clever you are. It is about what can ever be correlated with you. This returns us to the earlier chapters in a new key. The event horizon from accelerated expansion is not only a limit on travel, it is a limit on what can ever be measured, even with infinite patience and perfect instruments. Signals from beyond the horizon will never arrive because the space between us and them grows too fast. As expansion accelerates, more galaxies cross that horizon, one by one, like lanterns drifting behind fog. Their light redshifts, fades, and eventually becomes causally irrelevant. The sky empties, not because the universe ends, but because our causal patch shrinks relative to the whole. The edge approaches in time, which is a different kind of boundary than a wall in space. In visual terms, the observable sphere contracts in meaning even as space expands in size. The universe can grow without giving you more access. It can grow while taking access away. In that future, the cosmic microwave background also fades, not by vanishing, but by stretching. Its wavelength lengthens until it is larger than any practical detector can span, and its energy per photon becomes negligible. The fossils of the Big Bang become harder to read, as though the universe were erasing its own archive. Even the evidence for expansion can become inaccessible to late observers, because standard candles and distant structure disappear beyond the horizon. A civilization born in that far future could look up and see an island universe, static and lonely, with no obvious sign of a larger story. The edge would not be a cliff. It would be an absence of data. This is not just melancholy, and it is not just narrative mood. It is a physical statement that knowledge depends on horizons, and horizons evolve. The universe does not merely contain facts. It determines which facts can be shared, checked, and stabilized into science. Now the thermodynamic language becomes unavoidable, because it is the language of limits. Entropy is not only disorder, but missing information about microstates, quantified with precision. When you say a system has entropy, you're saying there are many underlying realities compatible with what you can observe. Black holes taught us that gravity counts information in a strange way, and cosmology suggests the same strange accounting may govern our entire patch. If there is a maximum observable entropy, then there is a maximum number of distinguishable states we can ever access. That caps ultimate knowledge, not by decree but by geometry. It also reframes the cosmological constant problem from earlier chapters without solving it. A tiny positive vacuum energy sets the horizon size, and therefore the entropy bound. So the value of dark energy is not only a dynamical parameter, it may be an information parameter, setting the storage capacity of our observable universe. This is where the word edge becomes more than metaphor and more than a feeling. The edge might be the boundary of a Hilbert space available to an observer, the finite arena of quantum states that can ever be operationally distinguished. In that view, asking what lies beyond can become operationally empty. If no measurement can ever distinguish alternatives, physics loses a handle, even if reality continues. That does not mean nothing exists beyond. It means our questions must be phrased in terms of what can be encoded, transmitted, and compared, because comparison is how science turns experience into evidence. The horizon then becomes a sensor, not of reality, but of testability. It draws a line between existence and evidence, and it does so without malice. The line is simply where causal contact ends, and where correlations cannot be established. Holography suggests an even sharper possibility, and it is hard to unsee once you consider it. If the bulk is emergent, then beyond the edge of space might not be more space. Beyond could be a different description, lower dimensional, where what we call distance is derived from entanglement structure. In ADS-CFT, the boundary theory has no gravity, yet it contains the bulk's gravitational dynamics. Gravity becomes a collective phenomenon, like pressure emerging from molecular motion. The bulk feels continuous, yet its deepest accounting may live on a boundary that never mentions depth at all. If something like that is true in De Sitter, then our cosmic horizon could play the role of a boundary screen. The universe would be a finite information system, with a limited number of degrees of freedom available within any causal patch. The horizon would not just hide things, it would define the size of the book we are allowed to read. But De Sitter holography is not settled, and the caution is part of the honesty. The analogue of ADS-CFT for our universe remains incomplete, and the technical obstacles are real. De Sitter lacks the same kind of boundary structure, and the notion of observables becomes more subtle when horizons are everywhere. So we hold two truths at once. Without forcing a premature resolution, holography is proven in some spacetimes, and it is suggestive for ours, but not yet established. Still, the direction of the clue is consistent across contexts. Wherever horizons appear, thermodynamics and information appear with them. That link forces a new reading of black holes as laboratories, and not merely as exotic endpoints. They're not only dead ends, but consistency checks for the universe.